Howdy y'all, we're back. This is the Diabolic vTutor. We're doing factoring polynomials. Basically, we're going to factor a variety of polynomials, including special cases, super tedious, higher degree polynomials with maybe degree 5, degree 4, uh, even degree 6s. So let's get started because it's going to be really annoying, at least some of the problems. Alright. So we've already spoken last time regarding the algorithms you need to factor out the special cases being difference of two squares. That one's pretty standard. And then the factoring by grouping, learning to recognize those ones. The difference of two cubes, and then the sum of two cubes, which require their own special things. Yeah, fun times with those algorithms, right? And are they super useful? No, but then the difference of two squares ones will pop up again. Factoring by grouping occasionally pops up. The cube ones, they sort of pop up here and there, just to surprise you every now and then. But probably difference of two squares is the most useful of all those special cases. But more on that as we come across, as we do the problems. So we're just going to be doing a bunch of problems today. Not covering the concepts per se, and I'll try to do a lot less narration. So first problem, we're going to start off with a 32. And then we're going to always take a quick survey of the problems. It's always a good habit to do. So problem number 1. First rule of factoring is always check all terms and see if they share common factors amongst all terms, and then you always factor those ones out first. And lo and behold, yes, we do have all three terms have some sort of x embedded inside them. So this has 3 x's, 2 x's multiplied together, and then just 1 x. So if we slap on the parentheticals, the most we can yank out from the x factors will be just 1x. Of course, checking the coefficients we have here. Fun times, we have 4 times 8, and then this one is going to be 6 times 8, and then this one is 6 times 9, right? Yeah, okay. Can we do, what can we possibly get? Well, there aren't any 3's in the 32, so you can't factor 3's from everything. This has a 4, this one has a 4. If we break down the 8, it becomes, oh no, we don't need to break it down because this one only has 2 times 3 times 3 times 3. Alright, so the most we can factor out in terms of the coefficient would be a 2 from all coefficients. So let us start by factoring something from all 3 terms first. We're factoring the 2x, again from all 3 terms. So divide by 2x to bring it out. 16x squared. Here we have the 48 divided by 2 is 24. Divide by x, exponent 1. Here we have the 54 divided by 2 is 57. Yeah, I mean 27, what am I saying? I just started, I'm already goofing up. We have 3 times 9, which is 27. Yes, divide by x, bring it out, close the parenthetical. Alright, so we have this kind of a grossness. It is a quadratic though. We have x power 1, x power 2 type, x power 1 type, and then technically x power 0 type. So use your favorite quadratic factoring algorithm. Unfortunately, these numbers are kind of bad. So to just do a quick check, I'm going to run it into the discriminant test to see if it's worth my time. To try to, actually, it doesn't seem that bad actually. Let me list the factors. So 16 and 1. 8 and 2, 4 and 4, right? Here we have factors of 27 and 1, 9 and 3, and that's it. So no perfect square here. What do we have that can, what combination can possibly produce a 27? Different signs, and the large with 2 magnitudes is positive. So let me check the intermediate ones first. As typical, so 9 times 4 is 36, and then here's a 12. What do you know? Of course I would pick the more intermediate values, right? Alright, so we have the 2x, copy paste that outside factor, and then factorizing this particular quadratic, both x's have the 4, so it's going to be 4x and 4x. And the factors of 27, we have a 9 and a 3. It doesn't matter where I put them because these are both 4x's. I'll put the 9 here since there's more space, and then the 3 there. Again, the two signs are different. So this product here and this product here, they have different signs, and then the larger of the two magnitudes is positive. This is the larger of the two, it's 36x, and then this is the smaller of the two, it's 12x. So I'll put the negative on the 9. So there it is, and then we have a positive here. And I think that basically confirms it. So this is 12x plus negative 36 is negative 20. Oh, what am I saying? I said it backwards. I'm sorry. I said the larger of the two magnitudes is positive. I don't know why I made it negative. So this is positive. This is negative. So that's why quick checks are pretty nice to do. So again, this gives us positive 36x, and then this gives us negative 12x. Verifies that middle one. So we're probably good to go in terms of the first problem. So this is pretty standard. Again, we have 3 terms. Factor something from all 3 terms first, revealing the quadratic. Once you have the quadratic, use your favorite factoring algorithm. And now this is a fully factored form. So good to go for first problem. I'm actually going to cross this out on this piece of paper so I don't accidentally recycle it, but for whatever reason. Okay. So, okay problem for the opening problem. Next up we have the 40x squared. This is quadratic. And then we have a plus a whopping 1,597x. And then minus 120. So this is honestly, again, I have some complaints regarding the x method. Sometimes, you know, you're going to have to multiply this one times this one. And you're going to get some chunky numbers. So I'd rather not deal with that. Well, first, check to see if you can factor something from all terms. Wonderful, right? So factors of 40, I might as well just list it out. 40 and 1, 2 and 20, no 3s, 4 and 10, 5 and 8. It loops back around. Those are all our possible factors of 40. Factors of 120, 120 and 1. You have 2 and 60, 3 and 40. Notice going in order, of course. And then 4 times 30. Wait, what did I say? This is 40. And then 4 times 30. Always go in order. 5 times, what is that? 24? Yeah, 24. And then 6 times 20. No 7s, no, oh, there's an 8. 8 times, you still a 2 from here, so times 2. This is okay, 15. So you can kind of recycle your earlier work. So that's 8 times 15. Anything else? This is basically 3 times 5. And then that is 2 times 2 times 2. Do we have something more intermediate? Yes, we have a 12. 12 times what? 10. Oh, I think that's it. The fact that these two numbers are so close together, that probably means we've hit all the factors. So a ton of factors. It's not particularly nice. I don't really want to factor out this 1,597, but let me see. This is 6. This is 16, and then 6 plus 16 is not divisible by 3. So this is not divisible by 3. It's not divisible by 2. So is it worth trying to factorize this? I'm not going to try to factor it because it looks like a mess. Okay, so I will instead just go with my standard factoring algorithm. This is just the basic quadratic. X squared, x power 1, x power 0. So we want to play around with these candidates and get this huge intermediate value right here, 1,597. So let me pick an intermediate thing here and then an extreme value here, and then we'll see what happens when those ones converge. So we have 4 times 10-ish, which is 400, and then 1 times 12 gives us only a 400 and a 12, which is a far cry from getting a sum of 1,597. So I have to pick more extreme values. So not this combo, right? Alright, so maybe we'll try this one, and we will try this one. Just to see, just to play around with the numbers. This is just gauging the problem. So we have 40 times 30 is 1,200. So that's pretty close. So looking pretty good. But that's not quite there yet. We'll pick this one. Okay, it's this one. It's this one. Because we have 40 times 40 is 1,600. And then 1 times 3 gives us a very nice 3. Okay, it is possible to get a 1,597 from the interplay of these two numbers. The two signs are different, and then the larger the 2 is positive. So this is positive, this is negative, which if you perform the addition, then we get 1,597. That's perfect. Okay, it kind of worked out. I got luckier than I thought. Alright, so again, those are the factors for the x. So we have 40x, and then we have singular x. Well, this 40 here has to be multiplied to that 40. So those two have to multiply, and then the 1 has to be multiplied. The 1x has to be multiplied to the constant 3. So 1x has to be multiplied to constant 3. There we go. Again, the two signs are different. The larger of the 2 is positive. This is the larger of the 2, but positive. Smaller of the 2 is negative. And we're good to go. Thank goodness I didn't try to factorize this because I don't know the factors of that number. Okay. Well, that's it. So 40 has no factors in common with 3 aside from 1. That's just a 1. So this is fully factored form. We are good to go. Alright. Good progress. So the first two are just quadratic problems. So next up we have 2x cubed minus 3x squared plus 2x minus 3. Alright, this is definitely not a quadratic because we have a 3 here and 4 terms. So not a quadratic problem. Some sort of a degree 3 polynomial. And not coincidentally, we have a 2, 2, and then we have a 3 and a 3. So, and then a negative sign and a negative sign. And we have an even amount of terms. So big clue, you factor by grouping. It's fairly straightforward for most problems, whether or not you factor by grouping. Again, anytime you have an even amount of terms, and then you have remarkable coincidences with the coefficients, it's probably factoring by grouping. But check to see if you can factor something from all 4 terms first, as a supergroup rather than small groups first. We have 2, we have 3, so no, we cannot factor coefficients from all 4. We have cubed, no x's, so we can't factor something from all 4 terms. That's okay. I am going to put these 2 in a group, and I'm going to put those 2 in a group. Those are not our only options, but that's the option I would choose because I don't feel like doing the other group. Alright, so grouping those 2, slap on the open parentheticals. We're going to choose to factor what common factors from those 2. It's just going to be x cubed. Again, this one doesn't have any 3s, this one doesn't have any 2s. This is x cubed, which is also in there. So factor out the x cubed. I mean x squared. So factor in x squared, we're going to get 2x. Factoring out x squared, we're going to get minus 3. This one, not much to be done. We're going to close the parenthetical regardless. This looks like multiplication now, so be careful. You could always put a positive right there. So I'm going to treat this as plus 1. And then remaining inside the parenthetical is still 2x minus 3. So be careful. Don't just slap it on here and don't put the symbol, because it's just going to be multiplication if you don't put the symbol right there. Just for visual clarity, let me delete this part real quick. So I want to put it in the unsaturated color. Oh, I can't even see. Wait a minute. Yeah, there we go. 2x minus 3. Close the parenthetical here, the red parentheticals. And then we take a quick pause. we notice that this here factor is the exact same thing as that here factor. So that's all according to factor by grouping plan. So putting on the brackets. We're going to factor out this entire chunk from term number 1 and then term number 2. Again, this here factor chunk is the exact same thing as this here factor chunk. So those are common to both inside terms, so we could factor out of the brackets, thereby getting 2x minus 3. Brackets. Leftovers inside is x squared plus 1. The color's nice for the visuals, I would say. But this is wrong. Don't write it like this, please, because this looks like this is the only thing that gets multiplied to the x squared plus 1. So you must put parentheticals. This is a complete answer, right? Nothing to factor here. This is the sum of what? 2 cubes, so you don't have an algorithm to factor this out unless you want imaginary numbers. So leave this alone. I'm just going to do a little bit of cleanup. We're going to have 2x minus 3 parentheticals. I'm going to drop the brackets back to regular, downgrade them back to regular parentheticals. And then we're done with this factor by grouping problem. Again, recognize that you have an even amount of terms, and then there's a remarkable pattern with the coefficients. So that's more visually obvious because you could just see it's a 2, 2, and a 3, and a 3. So more annoying factor by grouping problems, the coefficients will be a lot more varied or buried, or what's the word? It won't be as clear. The problem maker will try to obfuscate the similarities between them. But more on that when we actually get to other problems. So that one is finished. Factoring by grouping. Alright, next up we have the 16x cubed minus 42x squared plus 53x. Ooh, this is already bad. 53x and then minus 6. Alright. A few things to check. Make sure you check to see if you can factor something from all of them. There are 4 terms, so maybe factor by grouping. This looks really bad though. Factors of 16, 2 times 2 times 2 times 2. And the factors of 42, 2 times 21. Oh, that's awkward. 3 times 7. Factors of 53. I think this is a prime number. Let me think. Yeah. I think it is. Yeah. It's sandwiched between 54, which is factorizable, and 52, which is even number, also factorizable. But I don't think 53 is... It doesn't register. It doesn't ring anything. So I don't think this is factorizable. And then we have a 2 times 3. Okay. So this tells us a few things. Because this 53 doesn't have any common factors with anything else, including this 6, including this 42, including this one, probably not factor by grouping, even though we have 4 terms. So I think this is just a generic factoring situation with a polynomial beyond a quadratic. So it's going to have to do that annoying candidates of 6 divided by candidates of 16 type of situation. All right, and a few other things to make note. This is a cubic function, so we are guaranteed one solution somewhere along the way. And using Descartes' rule of sign, we have a positive change sign, change sign, change sign. Oh, that's bad. So that's a 1, 2, 3. 3 sign changes. Oh no, that's good, because there are 3 sign changes the way it's written. Let's say this is a function, right? Because there are 3 sign changes the way as it's displayed. That means that there could be 3 positive real solutions, or there could be 1 positive real solution. But we're guaranteed 1 because this is a cubic function, so this must be true. So we have 1 positive value that is a 0 for this function. So what is it? So I'm going to keep note of that. And again, let us find the candidates of 6. It's going to be 1, 2, 3, and 6. over the factors of 16. That's just going to be 1, 2, 4, 4, 8, and 16. Going with a perfect symmetry, 1 times 16, 2 times 8, 4 times 4. So we know we've accounted for all factors, plus or minus. Okay, so like I said, we're guaranteed one positive one. We're paying attention to the way the numbers are changing. We have a 16 going to 42 to 53 to 6. Let's pick something fairly moderate. Let's pick a 1 and see what happens for the synthetic division. So if our 0 is presumably positive 1, we have exponent 3, 2, 1, 0. That's all terms are present and accounted for. So we have 16, negative 42, 53, and then negative 6. Make sure you copy this correctly, otherwise it's all your efforts will be for naught. Alright, follow the algorithm. We drop the 16. It's a very mechanical process. Ooh, this looks bad. This looks bad. Negative 26, right? Yeah, and then times this one. Maybe not the worst. It's kind of bad though. It's kind of bad. This is 27. Yeah, it's kind of bad. 27. Okay, it's not tremendously bad though. When you summate those two, we get positive 21. Because this is not a 0, therefore this is not a 0, and therefore x minus 1 is not a factor of f of x. So, okay, that's fair. That's fair. We can do better than that. Alright, hopefully I didn't screw up any of the signs. But this is just a cubic, so it's not terrible. So I'm going to start shrinking these things. Do we really need... Oh, okay, I guess we still need that. Let me just do a little bit of rearrangement. Again, we ruled out the 0 of 1, so we need another candidate to test out. Let's test some fractions. Let's test... Well, let's see what happens with the numbers, right? Why do we get such a big remainder? Because this is a big positive. Why is this a big positive? Because this is too small of a negative. The magnitude is too small for this negative. So that means we need to have a smaller thing right here, which means we need to go less than 1. Okay, so we gotta go less than 1. So let's go with 1/2. That's our next candidate. So we have 1/2 as a 0 candidate. Just copy paste all those coefficients. Wonderful. This is why we love factorizing polynomials. I guess some people like doing this if they're decent enough at it, right? It's like doing one of those number puzzles, like a Sudoku or something. And we drop the 16, multiply that as an 8. Ooh, yikes! And then this is a negative 34. Half of that is negative 17. That does not look good. Not looking good. And we have 6. Positive 36. Half of that is 18. Summing those two, we get positive 12. We're not quite there yet. Okay, so what has... Again, that means that this is... Because this 12 is not 0, that means that this 1/2 is not a 0. Because it's not a 0, then x minus 1/2 is not a factor. Okay, so we can't use the intermediate value theorem, unfortunately, since both answers have gotten... Both 0 candidates have yielded positive remainder, so not super informative, unfortunately. So let's try 3/4. That's maybe not 3/4. Something smaller than that, right? 1/4. Let's try 1/4. Well, why do we get such a big remainder here, right? Because this one is too large. We need a smaller thing. This needs to be the larger size negative, which means this one needs to be a larger positive, which means we need to cut this one less. Oh, so maybe 3/4 might be the better way. Yeah, let's go 3/4. So 3/4 as our 0 candidate. Standard procedures. I think there is another way of figuring out these values to test, but I don't remember it off the top of my head. So drop the 16. 4 times 3 is 12. Summate is negative 30. Ooh, this is bad because 30 is not divisible by 4, which means we get fractions, and then the rest of it is going to be terrible. But for sake of completion, should we do this? Yeah. Because I want to know what's the final signage here, so I can determine whether or not to use it's useful for intermediate value theorem. All right, so multiplying that one is something kind of awful, right? So what is this? This is negative 28, which is divisible by 4, and then negative 2. So multiplying that, we're gonna get negative 21-ish, and then technically we still have this junk right here. What's 3/4 of that? That is 1.5, I want to say, right? Because if you do -1, -1, and you do 3/4, that's negative 70.75 for each of those. And then you smash those back together, negative 1.5. Yeah, I think so. Yeah. So negative 22.5-ish. We don't need to be perfectly exact, though. I think this is right. I think so. Alright, and then summoning that, I'm just going to round this up to negative 23, because again, I just care about the sign result afterwards. Ooh, that's bad. Why he's going to be like this? Okay, same thing right here. We're going to get the same-ish product. It's going to be a positive value that's greater than this one in magnitude, so our final answer is positive in the end, which again isn't super useful. So unfortunately, we can't use intermediate value theorem yet again, unless I screwed up the math somewhere. I really hope I didn't. And this is only like a degree 3 polynomial, it's not even like degree 5. Okay, so that's what we have. Again, I don't, off the top of my head, there's nothing that we can do to really simplify this off the top of my head. So, unfortunately, it just didn't work out for the 3/4. Let's take a quick evaluation of why it did not work out, right? Let's see. This one is too positive, so this one is too large. This one is not large-sized enough. This one needs to be large-sized, so this is cutting it not enough. This is cutting it too much. This is cutting it too much, and this is cutting it not enough. Right? Okay, so we need something between 3/4 maybe and 1/2. So what is between those two? Is it 3/8? Yeah, let's try 3. No, 3/8 is less than 1/2. What am I saying? It's gonna be between those two. 0.5 and 0.75. I really hope I didn't screw up the math here. Right. Okay, well, let's not be paralyzed by indecision. Let's just pick something 3/8. I know I said I wasn't gonna pick it, but this should be easy to eliminate, right? So drop the 16. What I'm doing, I'm going to populate the rest of this. Alright. Perfect. And then we have 2 times 3, which is positive 6. That's going to be a negative 36, which is not divisible by 8. So big clue that this is going to be the wrong one. But for the sake of getting the signage here, so we could use intermediate value theorem maybe. Let's have to trudge on. So this one divided by 8. That's approximately 8 times 4, 8 times 5. So 4-ish. So 4-ish times 3 is 12. So let's say 13, just for funsies. Summate those two, we get 40-ish. And then multiplying that is 5 is 15. It's still positive. What do you know? So not super useful yet again. Okay, well, tons and tons of, unfortunately, not very useful situations. Alright. That's a pretty small positive. Maybe something smaller than that. Let's try 1/8. Yeah, I don't know. I'm getting desperate at this point. I'm going to wish I had a better algorithm than this guess and check. I'm pretty sure there is one. I just don't know it. Alright. Drop the 16. Multiplying that is 2. Summating that is negative 4. Okay, so that looks pretty good. So far, so good. So then we have negative 5. Oh, you know what? I think we got it. We got it. Perfect. 1 times that is positive 6. What do you know? 0. Excellent, excellent, excellent. Alright, cool. So that means that because this one produced a 0 remainder in the end, that must mean 1/8 is a true 0 of the function f of x. And therefore, because it's a 0, you can convert it into a factor. So x minus 1/8 is a factor of f of x. All of these are divisible by 8. So, but then they're also, don't forget, these are coefficients for these ones after they got divided by this. So this one, x cubed divided by singular x, exponent 1 gives us exponent 2. So this is a quotient that is a quadratic after you divided f of x by this. So don't forget that. Never forget what this actually means. Alright, this is just a plus. Again, these are all factorizable by 8. We're gonna factor on 8 from all 3 terms, and we're gonna slam dunk it right here to beautify the factor. So factor out the 8 becomes 2x squared minus 5x plus 6. Perfect. We'll take that again. Slam dunk it to that one. And we're subsequently going to get 8x minus 1. Quantity of this thing. Oh, this is a quadratic. Is it factorizable, though? This one's easy to do discriminant test, so let's check it out. So 25 and a minus 4 times 12 is 48. So this is going to get us a negative result inside the radical, which means there are no real solutions, which means that this one doesn't have any real factors. So we're going to leave it alone. 2x squared minus 5x plus 6. Fully factored form, I believe. This is just exponent 1, so that's good. This is exponent 2. But again, we already checked the factorability of this quadratic. And it's not factorizable because the discriminant test tells us that it's not factorizable because negative inside the radical. No real factors here. So that is good for this particular problem. Look at all that work. But we got lucky on this one. Again, we need to test positive. We knew to check for positive zeros because we're guaranteed one solution, and then using the Descartes rule of sign test, we saw that we're guaranteed at least one real positive solution. One real positive solution that makes a 0 for the function, which is going to help us out in factoring. Okay. Let us delete that and cross it out. Oh, it's a lot of problems. And then next one up, we have 12x to the power of 5. Yikes. See that? That's the stuff of annoyance. And then minus 32. X power 4. And we have plus 27x. And lastly, minus 72. Alright. So pay attention to the number pattern. I suspect this might be factoring by grouping, because number 1, I made the problem. But number 2, it looks kind of similar. These ones look like they're closely related. These ones look like they're have some sort of common factor. But, you know, always check. Always, always, always check. Move it up. Okay. Here's what I mean. What are the factors of 12? 2 times 2 times 3. Factors of this one, it's just 2 to the power of 5. Ooh, those are just 3s. That's nasty. Factors of 72. That's 9 times 8. Yeah. Alright, well, again, my suspicion is that this one is going to be a good group, and then this one's going to be a good group. Because the x's are abundant there, and then this one has few x's. So, That's the idea. We can factor out a 4 from those two. We can factor out a 9 from those two. We'll be left over with an 8 here, and we'll be left over with an 8 here, and a 3 there, and a 3 there. Perfect. This is definitely a factor by grouping problem. Not because I wrote the problem. Well, kind of. Alright, but it's just suspicions. Now, again, the suspicion is you have an even amount of terms, and then there is a remarkable similarity amongst some of the subgroups. Again, this one has high degrees, these ones have low degrees. This is a minus, this is a minus, this is a plus, this is a plus. And checking the factors confirms it, right? Okay, so from those two, they have the 9 common to both of them, so factor out the old 9. It's a positive 9, of course. And from those two terms, they have common the 4 and the x power 4. Alright, so after factorizing those ones, what are we left with in those parentheticals? So 12 divided by 4 is 3. Downtick the exponent down to 1 exponent. Then this one is negative still. Divided by 4 is 8. That's just 1. 27x divided by 9 is 3x. That's looking good. And then we have the negative 72 divided by positive 9 gives us negative 8. So, as we hypothesized, it's a good factoring by grouping. So let us slap on those brackets. And we have term number 1 separated by plus from term number 2. Both of these terms have this chunky factor. We can therefore factorize that chunk from both of them and put it on the outside. So 3x. So 3x minus 8. Make sure to put it in parentheticals, otherwise it's going to be wrong. And then we have the brackets 4x. 4x power 4 and then plus 9. At this point, take a step back, check something real quick. This one is just exponent 1, so not much to do with this particular situation. This factor is done. Right here, we have a perfect square, we have a perfect square, we have a perfect square, but it's a positive between those two, so we don't have an algorithm. It's not a difference of 2 squares. So this one is done. It has no real zeros. So, in conclusion, we are done. So 3x minus 8 times 4x power 4 plus 9. Just to connect this with your graphical sense, if you decide to graph something like this, this is going to be something like a parabola looking thing pointing upwards, stretched upwards, both pointing, well, it's positive 4, so it's stretched upwards. And then we have a plus 9, so it's just shift 9 spaces upwards. So it's something like this. So as you see, no intersections with the x-axis. So no real zeros, which means no real factors for this one. Which means we're done. Yes. Perfect. Nice, nice, nice. Next problem up. It's honestly kind of disgusting. I'm just looking at it right away. It's pretty bad. We have 6x. Oh, okay, never mind. It's not too bad. It's just the leading coefficient is 6. Not the worst. At least it's not like 64. 64 would be a real pain, honestly. And then we have 11x cubed minus 2x squared minus 26x, and lastly minus 24. So we have 1, 2, 3, 4, and 5. We have 5 terms. It's not a good looking situation for factoring by grouping, but can we force it? Can we force factoring by grouping by splitting the middle term, right? Can we do that? Let me think. This is going to be factors of 2 and 3. This is, oh, this is, okay, this is bad. The fact that it's 11. And this one we can theoretically split. This one factorizes into 2 and 13. This one factorizes into 2 times 2 times 2 times 3. 4 times 6, yeah. So unfortunately, even if we somehow split this negative 2x squared to match those two, and then to try to match those ones, I don't think we can get an optimal factoring by grouping situation, because this 11 here sucks, and then this 13 here is, they're in disagreement. If this had been an 11, and then this is also 11, that might be cause to try to split this to factoring by grouping, but it ain't happening. I'm sorry. That's the reality of life sometimes. Sometimes you can factor and sometimes you can't. So what does that leave? What kind of recourse do we have at this point? Again, this is a weird 11, so we can't factor something from all 5 terms. This is x power 4. There's no x power... Oh, there's x power 0, but that's not useful. So we have no choice but to proceed down standard generic polynomial factorization. So basically come up with the candidates. What are the factors of 24? 1, 24, 2, 12, 3, and 8, 4, and 6. And because these numbers are close, that's probably it. And then we have factors of 6, 1, 2, 3, and 6. Plus or minus. Alright. Oh, unfortunately, it is an even degree polynomial. Degree 4, which means we're not guaranteed any sort of answers, which is a real shame. But let's use Descartes' rule of sign real quick. This is positive, so no sign change. This is 1 sign change. Oh, we have 1 sign change for the situation, which means we're guaranteed 1 positive real solution. So that is how we're going to start. The coefficients don't snowball very much, so we're going to pick a small number. We'll start off with the generic 1, just to see how the number crunching results. So copy paste. This is 4, 3, 2, 1, 0. All terms are present, so just steal the coefficients. Copy paste them. I don't endorse stealing, so we drop the 6. Standard algorithm, fun times. Ooh, this is looking okay. It's not the worst. And this is going to be 15. See, it's not that bad with the 15 subtracted from this one. So we have a negative. Oh, but it's going to be negative though. Okay. I see. I see it. And then we have negative 11. Summate that. We get a whopping negative 35 remainder. What does that mean again? Because this is not 0, that's not a 0. Because this is not a 0, x minus 1 is not a factor. Alright, so that's going to be maybe informative. So what does that mean for us? Why did we get such a large negative value, right? Because this is negative. Why is this negative? Because that's negative. Because this is not big enough. Why is this not big enough? Because this in here is not big enough. This one's not big enough because this is not big enough. So we need a number greater than 1? Interesting. Let's pick 3 just to see what happens. So if we choose 3 as our 0 candidate, let's see what happens. Is that correct? Yeah, that's correct. Drop the 6. 18. 29. 30 times 3 is 90. 90 minus 3 is 87. Yes, 87. Summate. Ooh, this is looking bad. This is looking bad. That's okay. It'll be informative though. See that? That's bad. That's a positive 255, right? 24 plus 15-ish on the back. Yeah. Summate those two, we get a big positive. I'm going to stop doing it here because this is going to be a big positive. So end result is big positive, and this is actually very informative. Picking this as a 0 candidate gets us a negative remainder. Picking this one as a 0 candidate gives us a positive remainder. Therefore, between the values of 1 and 3, there must be a 0 between those two values. This is referred to as the intermediate value theorem. The idea stems, well, I guess the idea is most readable when you see a graph. So if you have a positive value here and you have a negative value here for your graph, for example, and your graph is definitely continuous, then you can see that as you connect these dots in any sort of scheme, as long as it's continuous, you have to cross the x-axis at some point, right? No matter how you connect this, you can cross in multiple points, but you're guaranteed 1, 0 between value number 1 and then value number 2, in which case it's positive 1 and positive 3. So the easiest one to test is probably positive 2. That's a 0, right? I don't think I chose that as a 0, honestly, but let's see. I think when I design problems for later problems I make, I don't pick x minus 2s usually, but let's see. So there's that. This is going to be 23. Yeah, that's looking kind of bad. This is... Oh no, because this is kind of large. No, this is too large. It's already too large, but that's okay. Which means our end result is probably positive. But let me trudge through the work. Yeah, it's too large. Too large. Big positive in the end. Okay, so we can narrow it down. Basically, because this one produced a positive remainder, and this one also produced a positive remainder, we can narrow the goalposts. So there must be a 0 between 1 and 2 because of intermediate value theorem. So shrink that. Okay, so what number candidate of here is between 1 and 2? Well, we do have 2/3. Okay, I'd probably pick 2/3 as a 0, let's be honest. Probably, right? Let's see. I know myself well enough. I think I wrote these problems a day or two ago. Almost messed up there. Okay, drop in the... let me make this a little more compact. Alright, drop that down. Product is going to be, what is that? 2 times 2 is 4. Summate is 15. Okay, this is looking good. The fact that this is divisible by 3 is looking good. So multiply those. It's 10. Oh, no, it's bad. It's bad. I spoke too soon. 2/3 of 15 is going to be 10, right? Yeah, but if you summate that one, that's an awful 8 because 8 is not divisible by 3. But let's continue on because it could be useful. So 8 divided by 3 is less than 3. Is like 2 point something-ish times 2. It's like 5-ish. So it's a small positive essentially. So let's just approximate as positive 5. Summate, we get a big negative still. Product is going to be a negative. The result is negative. This is informative still because now we can narrow the goalpost to 2/3 and wait, what was it? 2 got us a positive 0. 23 got us a negative 0. So it's a value between 2 and 3. So we can ignore the 1 at this point. So according to intermediate value theorem, we're homing in on the answer. It must be between 2/3 and 2, unless I screwed up the math. Again, you always hope that you didn't screw up the math somewhere. Especially matrices. Let's see. What do we have? What's between 0.67-ish and 2-ish? Oh, 3/2. That's probably something I would pick. It's either 2/3. I'm sorry, it's either 3/2 or 4/3. Let's pick this one. I have a sneaking suspicion it's 3/2. Alright, here we go again. Just following the algorithm. At some point it feels somewhat relaxing unless you're taking a test. Then it's absolutely annoying. We have 3 times 3 is 9. Summate 20. Okay, that looks okay. And then 10 times 3 is 30. Summate that is 28. That's still okay. 14 times 3. I can't do that in my head for some reason. Oh my goodness. 14 times 3, 30, 12, 42, right? I hope it's 42. Let me check that real quick. 14 times 3 is 42. Yeah, 42. Yeah, what am I saying? This is going to be 6 times 7. Yeah, it's 42. Yeah. I should know that. Summate those two. We get positive 26. Ooh, is that? No, it's not quite right, but we're very close. Let me make sure that's correct. That is 50. No, that's not right. Oh, thank goodness. This is like this. Almost screwed up. Okay. Yeah, that's good. Looking good, looking good. Okay, so 8 times 3 is positive 24. We've done it. There it is. Remainder is 0. Perfect. So 3/2 is a 0 because it produces 0. Wonderful naming scheme. So therefore, x minus 3/2 is a factor of this polynomial. The leftover, this quotient here, is degree 3 first. So this is 6x to the power of 3 plus 20x to the power of 2 plus 28x plus 16. You can see that all these share a common factor. We can probably yank that out and multiply to this junk to make it look beautiful. So let us factor out probably just a 2, right? This is a 2. This has a 2 and a 3. There aren't any 3's, so we could just factor out 2 from all 4 terms here, and then we'll multiply that 2 to in here. So factoring out the 2. Whoa, almost messed up. Oh, I was just going to copy these straight up. Oh, we went 2 in the zone. The wrong zone, of course. Copy paste that. And now we will distribute to those two to beautify the answer. So therefore 2x minus 3. And then left over is this junk right here. So we have 3x cubed plus 10x squared plus 14x plus 8. But we're not done though, right? All we have here is factor number 1, which is fully factored. Factor number 2, which is kind of dubious. Because this is cubic, we're guaranteed one real solution. It may or may not be nice. So there's a little bit more work to be done with this one. So we can generate a new set of candidate. We can repopulate the candidate list and proceed with more synthetic division. But let me check something real quick. Can we factor by grouping? I think if you can't factor by grouping in the beginning, you still can't factor by grouping afterwards, I believe. But let me check anyway. This is factors 3. There aren't any 3's here, nor here, nor here. So yeah, we can't factor by grouping, probably. Yeah. I don't think so. So this one is just going to be standard situation. Again, we're guaranteed one solution. We have a positive, 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 positive. We have no more positive real solutions. So we must check the negative situation. Yeah, so we're guaranteed one negative solution. It may or may not be rational. Okay, so I'm going to repopulate the candidate list. So factors of the back divided by factors on the front. So 1, 2, 4, and 8. Factors of 3, 1, and 3. And do recall that the factors that we have used before that have failed, this 1 here, this 3, this 2, and this 2/3, they will not work for this one again, so you don't test them ever again. And also, I made note that using Descartes' rule of sign, you don't have any sign changes, so therefore there shouldn't be any positive ones, which should also disqualify those ones. So what I'm saying is never use the ones you've already used. That did not work. If this one works, it may work again, but we don't have any 3's on top. So this one is done. Alright, I just want to make a quick note of that. So let us get to factoring this junk. And now we need a negative, so I'm going to try -1. It's a classic move, honestly. Copy paste all the factors, but make sure all terms are present and accounted for. Yes. So 3, 10, 14, 8. Drop that times summate times summate. Hey, that's actually very close. +1. What do you know? Alright. So we're very, very close. We need a slightly bigger number. So we need a slightly larger sized, a larger magnitude negative that's a little bit above -1, which is going to be what? 4/3? Yeah, I think we'll try positive. Oh, we'll try -4/3 because I think that's going to be it. So shove that off to the side. Let us now try negative 4 over 3, and I think this is going to do it. So 3, 10, 14, and 8. All right, drop that. Products. Sum. Products. Yeah, look good. Looks good. Looks good. Yes, 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 yes. Oh, perfect. See, told you. So now we get a 0 right here. Perfect. Which means that this is a 0, which means that x minus 4/3, which is plus 4/3, is a factor of this quotient of this polynomial. Alright, and then the left over here is just going to be a simple quadratic. As you can see, all these coefficients, all 3 coefficients for the quadratic can be factored by 3. Perfect. So again, this is going to be 3x squared. This is plus 6x plus 6. You don't have to write this down, but I'm just writing it just for clarity's sake. So factor of 3 from all 3 terms. I'll just jump to just factoring out the numbers to begin with, honestly. And then we'll take this 3 and distribute it to that junk right there. Distribute. And be careful for this particularly common pitfall of just excluding the first factor that we've found. That's a lot of F's. First factor we found is... I like that sound. It's poetic, right? Some sort of a... What was it? Alliteration? Yeah. Fully factored form, but don't forget about the factor you found before, which is right there. Don't forget that one. Very easy failing. Alright, I think that's correct. That's a very sloppy quick check. We have 2 times 4 times negative 3, which is negative 24. Yes. We have the x cubed times 3x times this one, which gives us 6x power 4. Okay, that's a real quick dirty check. Oh, we still have a quadratic here. It doesn't look factorizable, though. You can... Oh, no, wait. Is this factorizable? No. Factors of 2, 2, and 1. Okay, no. But use the discriminant test. So, b squared is 4. Minus 4 times c times a. So we're going to get square root of a negative 4. So this one doesn't have any real solutions, but it does have imaginary solutions that are fairly nice. If you don't care for imaginary solutions, this is going to be fully factored form. But if you do care for imaginary solutions, let me just factor this out real quick. It is going to be... I should not delete this. Yeah. Okay. Since the discriminant test produced a square root of negative 4, this one is actually, quote-unquote, a nice answer that is reportable. Negative b plus or minus junk all over 2a. Again, you can't take the square root of a negative value, but you can just hide it under the carpet. You split it into root 4 times root negative 1. This one you can take the square root of. It's just going to be 2. Again, this one is you can't take the square root of that, so you just obfuscate it by hiding it. Like, oh, you just hide it under the floorboards. We have a plus or minus in the front, and then 2. Everything is divisible by 2. What do you know? So divide by 2, divide by 2. So negative 1 plus or minus I. So we have 2 roots there. Make sure you know how to capture this into factored form. We need to split this manually, so it splits into negative 1 plus I. Is our first 0, and then our second 0 is going to be negative 1 minus I. 2 imaginary solutions. You just need to subtract them from the x as standard procedures. Minus. My preference is just to leave the parentheticals on. So changing this into a factor, we also get x minus negative 1 minus I. So again, I prefer to keep the parentheticals and not distribute these two. Not distribute that one. So I would do this one times this one. Times this for fully factored form with imaginary factors. But again, if you don't care for imaginary solutions, because you know that's not what your teacher asked for, then you stick with this one. You stay with this one. That's fully factored form. What a bunch of work, right? You see that? Ugh, disgusting. Moving on, of course. Let us. Where are we? Wait, what was that? 6 and 11 and negative 2. Okay, crossing this one out. Alright, moving on. Next problem up, we have the x power 6 minus x cubed plus x squared. And then minus 1. There you go. Alright, you can take a guess, right? If you look at this, what kind of factoring method do we probably have to employ? Well, 1, 2, 3, 4 terms, right? There's remarkable similarities between these ones. You know, this 6 is twice that of 3. This one is, oh, it's not twice this one. It looks very similar, you know, if we could factor out x cubed from those two. There is a minus here, and there's a minus there, so that's an awful good suspicion to act on. This is factor by grouping. So we shall arbitrarily group those ones and those ones. Can you do another type of grouping? Yes. But I choose to do it the most straightforward way, which is this way, I would suppose. So from those two, we could factor out x cubed. And what remains inside the parentheticals, x cubed minus 1. Ooh, that's interesting. Close parenthetical. And then around the parenthetical number 2, we could factor out just a positive 1. So in the parenthetical is going to be... Oh, this is not right after all. Oh, no. Okay, well, I was mistaken. Alright, so unfortunately, factoring and grouping was not the way to go for precisely the reason this one is twice of that, but this is not twice of that. Yeah, so interesting. Let me ponder this for a moment. I didn't screw up anything, did I? 3 plus 3 is 6. 3 plus 0 is 3. Yeah, okay, so this ain't factoring by grouping after all, right? That's a real shame, though. I thought it was going to be the situation. So, no factor by grouping. The initial suspicion was wrong, but it was just a suspicion. But I think the factorization is easy. This is just a 1 and a 1 in the front. So, if it can be factored, then it should not be very difficult, because we literally have few candidates. Factors of 1, 1. Factors of 1, 1. So, plus or minus. Using Descartes' rule of sign, we have 1 sign change, 2, 3. So we're actually guaranteed 1 positive real 0. So let's do positive 1. Such is the power of Descartes' rule of sign. Oh, we gotta backtrack. 6, 3. So okay, we're missing some terms. So if we were to fully expand this out, this is 0 x power 5. Almost goofed up. 0 x power 4, because we need to account for all terms, including invisible terms, after degree 6. Otherwise, your algorithm machine will fail because it's a dumb machine. Alright, so we have power 4, and this is going to be minus x cubed. This is present. This is present. Maybe we can factor by grouping here? No, we can't. Not that I'm aware of. But, you know, we already know that the positive one should work, because we're guaranteed 1 solution. So there's a very high chance this positive 1 is actually a 0. Let us extract the coefficients. So 1, 0, 0, negative 1, positive 1, negative 1. Alright, here we go. Okay, this is just... Be careful. Some people accidentally multiply these to produce 0, but it's always summed down. Yep. Yup. Yup. Nice. Nice. That's what I expected. Yeah. Alright, so this is a 0 because it produced 0. Therefore, x minus 1 is a factor of this thing, and the result is this. This is a quotient. This is degree 1. We took out a degree 1, so we have a degree 5 right here. So this one is x power 5, x power 4, x power 3, x power 2. I'm going to put that right here. X power... Wait a minute, did I screw up? That's weird. Wait. 1, 2, 3, 4, 5. That seems really weird. Something's not quite right. Why do we have all x's? That is very weird. Let me double check something. 6, 5, 4, 3, 2. Oh, I forgot 1. Okay, that's why. You see, the number crunching machine fails if you forget one term, which I did. It's going to be plus 0x to the power of 1, and this is technically x to the power of 0. So this one screwed up the machine. But we'll still end up with 0, I'm sure. Let us expand this real quick. So where was the error? Between positive 1 and negative 1. So this one we need to move it over with 1 space. Alright. The coefficient here was 0. Yes. So this one times this one is 1. Summate is 1. Multiply is 1. It's consistent. It still sums to be 0. And that's correct. Alright, cool. Which now means this is correct. This is correct. Still correct. This is still correct. This is still correct. And we're going to have a constant 1. Okay, there you go. There you go. There you go. So the reason why I knew something was up was because all of these have an x term, which means you could factor out an x from all 5. But that cannot be because we didn't have an x that we could have factored from all 4 right here. Alright. Just wanted to point that out. Did I screw something up again? It's supposed to be a plus 1, yeah. Yeah. Okay, so that's the quotient result. Don't forget to tack this on to have a complete answer. So we have up to 3 real solutions. We have this quotient that's left over. It's degree 5, so we could still have more potential answers, right? Let's test one again, since it's literally very easy to test. We only have one positive candidate anyway. So we're going to keep going. Make sure all coefficients are present and accounted for. 1, 1, okay. The 0 we're testing is positive 1 yet again. Drop that. Oh, you see, this is going to be wrong. How do we know this is wrong? Because all these numbers will always have to be positive. So in the end, you get like a 1. You're still going to get a positive 1. Okay, so now we know we need to test a different 0. It does negative 1. Yeah, that's the only other one we can perform, honestly. So negative 1 here, summate, multiply, sum, multiply, sum, multiply, sum. This is not good. Multiply. Ooh, interesting. Did I screw up this problem? Oh no, I wish I didn't. Well, wait, what is this? Oh, I forgot. Wait, what? I think I undid something. I forgot to place it. Well, that's just a 1. Ooh, almost messed up. So what? Yeah, this is not supposed to be here. Yeah, this is the original problem, right? Yeah, okay, so this is supposed to be here. Okay. Oh, okay, this is very interesting. We're still guaranteed one answer right here, right? We already pulled out the positive solution, but, Let me check something real quick. Okay. And then we have a negative 1 here to test. Let me crunch the numbers again real quick. Yes. 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 So, not a 0. Not a 0. That's kind of surprising. So I think at this point it is fully factored from what I can tell, but I don't feel this is quite right. I have a feeling I screwed something up somewhere. Either I've written the problem incorrectly, or I'm fairly confident this is correct, and this is also I'm fairly confident this is correct too. And remember, we only have those candidates because this is a candidate 1 only, and this is only a 1. So we don't have any other numbers to play around with. We already saw the positive did not work twice, and then the negative one as a 0 also didn't work. So I think that is it. This is a power 6. It might be doing something like this. No, that'll be a repeated solution. It might be doing something like... yeah, that doesn't make any sense. I must have screwed something up. Let me think. Let me think for a moment. Let me think. Oh, it might be doing something like this, where we have a positive 0 right here, and then we have we have 2 positive zeros. Wait, would that work? That means we have another positive irrational 0, but according to Descartes' rule of sign, we have 1, 2, 3. There can only be 3 solutions. So this, and this is an irrational 0 that's repeated twice. No, that's repeated twice though. That's weird. Yeah, that's really weird. Let me think. Okay, just for the sake of saving time, I'm just going to simply slam dunk this into a calculator real quick to make sure I wasn't led astray somewhere. So let me see real quick. X power 6 minus x cubed plus x squared, and then minus 1. Alright, let's see. Let's check the calculator. Yeah, I only have 1 real root. Okay, that's fair. Only 1 real root. I think that's it. Okay, I don't know why I wrote the problem like this. That's weird. I have a feeling I may have written something, copied it incorrectly. Okay, well, according to the calculator that I inputted this, we have a real positive 0, and then we have an irrational negative real 0. Okay, I guess that's fair. Alright, I think I'm just going to conclude this problem. It's not exactly my favorite, but at least the numbers are fairly straightforward. It's just a bunch of 1s. Okay. You know, this is really bothering me. Let me see my draft paper to see the problem that I actually designed. If I could find it. Oh, here it is. Oh, it's supposed to be a sum of 2 cubes. Oh, interesting. Okay, that's interesting. Okay, I think we need to take a step back. Okay. Well, I'm trying to think if this is worth exploring. Huh. It was supposed to be a factor by grouping problem. I must have written it incorrectly. I think that's what happened. Huh. Oh, okay, yeah. I wrote the problem incorrectly. But okay. So, long story short, the way this problem is written as is workable, and we got 1 solution, and that's it. So, let that be said. But the problem that I was supposed to write, it was supposed to be x power 5, not x power 6. Yeah, so let's explore that real quick. Okay, so again, as is, the way it's written, this is correct, but this is not what I had intended for the actual problem. So let us conclude this current problem, and then let me change it to the one the problem was supposed to be. So this here is a 6, but it was supposed to be a 5, exponent 5. So the mistake I made was when I was making the problem, I distributed it incorrectly, which is a common mistake. So when I did this distribution here, I multiplied the exponents to make 6, but we're supposed to add the exponents if we're multiplying the same bases. It's supposed to be x power 5, not 6. Wonderful. Okay, well, at least the problem worked out. But let us do this one instead. This is supposed to be the problem. Now it's going to make sense. So this one is 2 greater than this one, and then this is 2 greater than that one, which is x to the power of 0. Okay, now it's a good candidate for factoring by grouping. So group those two together, and then group those two together. Yeah. Okay, now it makes a lot more sense to me. So these two, you can factor out x cubed from both of them. See that? Yes. You could factor out a 1 from both of them. It's not super useful, but I'm going to write it here to make it explicitly clear. There you go. You see how this factor is exactly the same as that factor? So we have term number 1, which contains this factor blob. And then we have term number 2, which has that same factor. So we can factor this from both of them. Slap on the brackets. Factor that out. Thereby yielding x squared minus 1. Close parentheses. And in the brackets, we have leftover of x cubed plus 1. Yeah, this is supposed to be the problem. And some unfortunate souls would stop here and not receive full credit if this is like on a test, for example. The reason being, you gotta recognize this and you gotta recognize that. This is the classic sub-problem within your main problem scenario. So if you don't memorize, then it's hard to proceed forward. Pretty much. Yepers. Alright. So let us continue. This is not fully factored, and this is also not fully factored. This is a difference of 2 squares. It's just a quadratic. We want to produce a 0 in the middle. So it's the classic x plus 1 times x minus 1. Because again, this yields positive 1x, and then that yields negative 1x, which is perfect because these two will cancel, produce no term in the middle. So that is fully factored for the difference of 2 squares. Again, there are some unfortunate souls who would also stop here, but this is a sum of 2 cubes. This is perfect cube number 1, perfect cube number 2, summation between them. So this has its own specialized factoring algorithm, but because the coefficients are very straightforward, there's only 1x, then the factoring, you could also do it by synthetic division. You can kind of see already, how do you produce 0, right? How can you produce 0 by having x cubed plus 1? You know, just solve the math. So you subtract 1 from both sides. Take the cubic root of both sides. X is equal to negative 1. So we know this must be a 0. So you could just apply the long division to this polynomial right there. So negative 1 into, don't forget your invisible terms. This is going to be coefficient for x cubed, coefficient for x squared, coefficient for regular x, and then constant 1. Again, invisible coefficients. 0 coefficients for the invisible terms. Drop this. This is if you forget your sum of 2 cubes algorithm of factoring. You can circumvent that. Alright, left over. This is a cubic. We factored out 1x plus 1. Thereby getting a quadratic right there. So that's just 1x squared minus x plus 1. That's a quadratic. Is this quadratic factorizable? We'll check that in a moment, but let's not get too sidetracked. Again, copy paste those two. And this one here, we factored out a -1, which means -1 is a 0, which means x plus 1 is a factor. So don't put it right there. Don't forget your original factors from your difference of two squares. That would be tragic if you just kept your answer like this. Alright, this is a fully factored thing. Fully factored. Is this factorizable? Discriminant test. Well, maybe you could already kind of see it. This is factor 1, so you only get 1, 1. Can we produce a -1 from those two? No, we can't. So this one has no real factors, but, you know, just for sake of dredging up the discriminant test. Let's see. -1 squared is 1. Minus 4 times coefficient of a times coefficient times constant. So that's 1 times 1. Which is just 1. Which is just -4. So as you see, we get a square root of -3, which is not a perfect square. And it's negative. So no real solutions. No real factors. So this is fully factored form. Well, again, with real factors. So no imaginary numbers. Can we go on with this? Yes, you can. So again, if your teacher doesn't care for imaginary numbers, then this is our final answer. If your teacher does care, we can take this a little farther. It's not the best, though. So there are 2 strikes. You're going to get an imaginary solution, 2 imaginary factors, and they're not going to be rational either. So double strike, that's okay. And then we have -b plus or minus this junk here all over 2a. So those are your 2 zeros, but we need to split those 2 answers. Yikes. Disgusting. Subtract this from the x. That's going to be your imaginary factor number 1. If you're lazy, you could just put plus or minus like that one. Technically, this is 2. There are 2 answers here. But I'm going to explicitly write out the second one. So it's going to be x minus this other junk. Alright, so those are the 2 imaginary solutions with irrational parts to them as well. So this here thing factorizes into that there thing. So if you need to include imaginary factors, then those will be your 2 factors times your 3 real solutions, factors. And that's it for this particular problem. That was the way it was supposed to have been written, but I had, again, instead placed a 6 here. That's okay. It was a useful detour, so to speak. But let us move on. There's still a lot of problems. We still have quite a bit. And that's perfectly fine. Alright, next problem up. We have the dreaded 64 coefficient in the front. Disgusting, because there are many factors of 64. So we have x power 6, and then plus 30... Oh, no, 432. Wow. What was I thinking? Cubed? Yeah, that's an unusual jump. And then we have... Oh, no, okay, this is not too bad. Okay, I thought it was worse. 729. This is just a quadratic problem within the main problem. Yeah, okay. There are only 3 terms, so it's a classic trinomial situation. That's a quick survey. This exponent is twice that of this one, and this is technically exponent 0, so this falls within the quadratic situation, even though it's exponent 6. Okay, but again, the big clue that this is twice of that. So if you want to make this look more like a quadratic, you can. If you use u substitution, you can say that u is equal to x cubed You don't have to do this, but once you do it, you more clearly see why it looks like a quadratic. So here is the what's the word? We put on a mask. If we swap it out, we have this classic quadratic right here. So it's just a quadratic, essentially. But the question is, can we factorize this junk? You could use discriminant test. These are really bad numbers, though. But I think this is a gimmick, right? This is 64. What factors constitute 64? 64 and 1, 2 and 32, 4 and 16, and no 5, no 6, 8 times 8, yeah. So those are the candidates for this one. If this is a perfect square situation? What are the factors of 729? I don't know. This is 9 plus 9 is 18, and 18 is divisible by 3, so this whole chunk is divisible by 3. Wonderful. Oh, it's divisible by 9, actually, so let's do that. Divided by 9, we're going to get 81, which is also divisible by 9, so it's 9. Hey, that's nice, right? We could split this 9 into times 3 and 3, so therefore, this is a perfect square. It's just 27 squared. Okay, I think that's the gimmick. Yeah, it's probably this one times this one, right? 8 times 27 is what? I don't have a good algorithm for this, right? Yes. So 216. If we summate times 2, does that get us to here? I believe so. Yes. Okay, good. So this is just a classic perfect square situation. So if you take the square root of this one, which is 8, and you take the square root of this one, which is not as straightforward, it's just 27. And then you do 27 times 8 times 2 gets us 432. So you know this is a perfect square trinomial scenario. Wonderful. So it just becomes from the tedious work right here. Alright. What does that mean for us in terms of factorization? These must be the correct values breakdown for the 64, and then these ones must be the correct values of the breakdown for the constant. So the 8s go in front of the x's. And then the 27s are just hanging back right here. Same signs, both are positive. Easy. Why is this a perfect square scenario? Because this one times this one, they have the same bases, so you can just add the two exponents. So it becomes 8x plus 27 to the power of 2. Final answer. That was surprisingly easy, but then again I did write the problem, so should you really be impressed? No. Alright, that's it for that particular problem. Crossing it out. Oh, wait, I should not. I'm a little too hasty. Remember how I did U substitution? Yeah. Almost goofed up. So this is not the x. That is in terms of U. But if we put that back into there, we get this one. Ooh, yeah. Okay, here's the reason why. This is a sum of what? Isn't this a perfect cube? And isn't that a perfect cube? So this is, technically, you could factorize this even more. Okay, almost slipped up. So this is a perfect cube scenario. So it's going to be, what's the cubic root of 8x cubed? Again, this is 2 to the power of 3. You take the cubic root of that, it's just 2. This is x to the power of 3. You take the cubic root, that's just going to be 1x. What's the cubic root of this one? That is just 3 to the power of 3. Cubic root is therefore just 3. So we can factor out 2x plus 3 from this junk right there. So the algorithm, if you have the algorithm at your disposal and you just want to avoid having to do synthetic division, since this is just degree 1, let's just do the algorithm. So understand where these ones came from. Again, cubic root of that junk takes us here. Cubic root of positive 27 takes us to right there. What is this one squared? It takes us to this first term. Or squared. Then here is the tricky part. This one times this one, and then you have to flip the sign, will take you to this one. So this is a positive sign, you flip it, it becomes negative. 2 times 3 is 6. X is just hanging out. And then lastly, last term here is positive 3. Square that to get to the third term. It's positive 9. And then we're done with the situation. This is never factorizable, to my knowledge. Yeah. So after you factor the difference of two cubes, this one is the final thing you get, and this one is not going to be factorizable. Technically, all of this is getting squared. So this is exponent 1, this is exponent 1. We can use the distributive property of exponents, thereby getting 2x plus 3 squared times 4x squared minus 6x plus 9. Close that. Squared. Is this factorizable? I don't think it is. It's usually, I've never seen it factorizable. Let me use the discriminant test. So b squared is 36, and then minus 4 times, oh, it's already over 36, yeah. That's 36 times 4. This is definitely a negative discriminant, so this one is not, doesn't have any real factors. I know before I factored it regardless and got the imaginary solutions, but I'm too lazy. I would leave it like this. So let us be happy with this particular answer. This is now fully factored form. So be careful if you do u substitution, like this one. Don't just magically swap this back to a u like what I did right here. So this is, back to an x. So this is technically still u. Not u, but you know, letter u. There it is. There it is. There it is. No, this one actually is an x, because this one got back swapped. Yeah. Final answer, fully factored form with real solutions and rational coefficients. This is as good as it's gonna get. All right. Did I already cross that out? Yes, I did. Wait. No. Yeah, I already crossed that out. Okay. Moving on to the next problem, we have, what do we have? We have x power 5. That's already a good sign. We have coefficient 1 in the front. That's always the best friend. Like an old friend you haven't seen in ages. 1 coefficient is always a welcome sight. Minus 8x squared plus 32. Take a quick survey, please. This is x power 5, which is 2 greater than here. This is 2 greater than exponent 0. Suspicious. This is a 1 coefficient and a 4, negative 4. This is a negative and this is a positive. This is divisible by 8, divisible by 8, yielding 4 and 1. 1 and 4. Is that a coincidence? Most certainly not. So 4 terms, let's do factoring by grouping. Group number 1 and group number 2. From those two, you can factor out x cubed, thereby getting x power 2 minus 4. This is a difference of 2 squares. Always watch out for those ones. And from here, we can factor out negative 8 from here and here, thereby getting x squared plus, oh, not plus. Don't forget negative times negative gets positive. So that confirms that factoring by grouping was a good idea. Slap on the old brackets. We can factor from term number 1 and term number 2 x squared minus 4 factor from both of them. So bring those out to the front. Getting x squared minus 4, which is a difference of 2 squares, which we have to subsequently factor, don't forget. And within the brackets, what is this? That is a difference of cube number 1 and then cube number 2. So this one also needs to be further factored. Wonderful. This is fairly straightforward. Factors into x plus 2, x minus 2. Algorithms. Or just memorize it. So again, the two middle terms must cancel. This conjugate situation produces difference of two squares always. All right, this one again is a little messier. If you don't have the algorithm down. What's the cubic root of that one? It's just x. What's the cubic root of -8? That's -2. And again, here's the algorithm. Square that to get this one. X times -2. You flip the sign and you get this one. Lastly, this one squared gives you third term. And that's the algorithm. Again, if you don't care for that, this one is a fairly easy situation, so you can actually set it equal to 0. You can do +8, and then you take the cubic root of both sides. X is equal to 2. Since you have a 0, then you know that this is the factor, and then you can use synthetic division on this one. But make sure you account for all terms. So to do the setup, since this is a 0, you put a 2. Coefficient 1, don't forget there's a 0x squared and a 0x1. So 0, 0. And a -8 is right there. You'll see it's the same thing. Oh, almost screwed up. Thereby producing 0, coefficient 1, 2, 4, 1, 2, 4. That pretty much clinches it. And we are done for this problem. Again, I've never seen this one be factorizable before, so it's usually good. This is fully factored form, x power 1, power 1, power 1, yeah. Again, I've never seen it factorizable. So this problem is done. Not too bad. Next up we have, ooh, those are looking kind of gross. I put 3 stars by this one. Why? That looks kind of difficult. Alright, let's skip that for now. Let's do the standard one first. We have 80x cubed 232x power 2. Yeah. Plus 33x minus 189. Alright, so we have 4 terms. 1, 2, 3, 4. Maybe a good candidate for factor by grouping, but check the factors. Factors of 80 are 2 times 2 times 2 times 10. Factors of this one, ooh, that's kind of nasty, right? It's going to be 2 times 1, 16, which we can further break down. What is 116? 50 plus 8, 58. Yeah. 58 is divisible by 2 as well. It's going to be 29. Oh, that's weird. 29 is kind of funky, which means this is probably good. We can probably divide this by 29, right? I hope. Let's check it real quick. It times 6, right? No, it's not. Just kidding. I guess I was wrong after all. Well, at least it's divisible by 3, right? Divide by 3, we get 60. My brain's failing. Oh, there it is. And then 3 times 21. And then 3 times 7. That's not the best. That's not the best scenario, is it? Yeah, that's kind of unpleasant. Can we do something about that? Let me think about this for a moment. I don't think this is a good idea. Let me check this one again, just to make absolutely certain. Well, for sure this is 3 times 11. This one is a little gross. Well, okay, let's keep good practice. Can we factor something first from all 4 terms? I don't think so. This only has a 3 and 11. There aren't any 3s nor 11s, so already we cannot factor something from all 4 terms. So that's out the window. Can we factor by grouping? Well, even though the exponent degrees are looking good, it's the coefficients that are not good. So we have a bunch of 2's and a 5, a bunch of 2's and a 29. So this one right here, you know, if we had a 5 here and we had a 29 here, that would be a good candidate situation potentially, right? but this is a far cry from 11. There's no mixing and matching that we can possibly do. This 5 here ain't matching that. This ain't matching this. No match, no match. So from off the top of my head, this does not look like a good factoring scenario. So I think we've no choice but to do the standard procedures for factorizing polynomials of degree greater than 2. So this is just going to be find the candidates of 189 divided by candidates of 80. Those will be your 0 tests. So here we go again. Factors of this one. Luckily I already wrote it out, right? So factors of 189. 1 and then 189. It's probably not this one, right? 3 is the next factor. 3 times 42. The next smallest one is 9, and then 9 times 21. Next one up is, oh, I skipped the 7. 7 times 27. Yep. So 7 times 27. Do we have anything else? I think that's it, right? 9 and 3, 7, 21, yes. 9 and 21, yes. 27, yes. Okay, I think that's it. That's not the best, not the worst either. Alright, so divided by candidates of 80, that one's pretty bad. This is 10 times 8, yes. So we have candidates of 80, 1 and 80, 2 times 40. Smallest one next is 4. 4 times 20. Next one is 5 times 16. Smaller one up is 8 times 10. And I think that's it. Since these 10 and the 8 are very close, I believe we've accounted for all factor candidates. Let me double check that real quick. There are no 6s, no 7s, no 9s. So it should be correct. Or let's move. Let's move. That's a lot of stuff, plus or minus. Alright, so those are all our possible candidates. I have a feeling this is some sort of factorizable situation, right? Yeah. Let us do Descartes' rule of sign real quick. This is a positive, so no sign change, no sign change, one sign change. So we're guaranteed one positive real solution, exponent 3, yes. Okay. And these numbers are actually pretty atrocious, right? I think we need a fraction, because if we do the standard pick of 1, I think it's going to snowball into a really big positive situation. Right? This is going to be 80, and then this is going to be like 300, this is going to be 360-ish, and then it's going to be too large. So we need a fractional situation. What do we need? Let us try 1/2. It's very easy to test, right? No, I have a feeling we need to cut this down even more, because we're going to go 80, 40, and this is 270. That's like half of 270 is like roughly, what is that roughly? 140, 170. Oh, you know what? This actually might work. Let's see. Drop the 80. 40. 272. Half of that is 136. Summating is 169. Not nice, because half of that is not good enough. And it's odd. Okay, well, it's good to know though. We're going to get a small positive, so when you summate, we get a negative remainder, which means 1/2 is not a 0, which also means x minus 1/2 is not a factor. So put that off to the side. What has failed in this situation? Actually, 1/2 cut the number too much. So we need something slightly bigger than 1/2. Maybe 3/4. That's probably correct. I have a feeling I chose 3/4. But let us see. So we have 80 to 32, 33, -1, 89. Alright. Drop that. Multiply. 20 times 36, yeah. And then multiply, summate those two, 292. This is divisible by 4, yeah. It's going to be 73. 73 times 3 is going to be 21,9. Let me double check. This is critical situation. Yeah. Alright, summating those two is thus 242. That's really funky. Oh no, this is not divisible by 4. Oh, that's bad. Okay, that's fine. Let's pretend this is just 240. So it'll be 60. 60 times 3 is 180. So we still get a negative answer. But it's getting very close though. You see how this remainder here is a larger size negative than this negative? Yeah. Which means 3/4 is very close. We're very, very, very close to the correct 0. We just need slightly bigger number right here, which means this one needs to be slightly bigger than 3/4. So what is slightly bigger than 3/4? Is it 4/5? No, we don't have a 4. Maybe 7/8. I think let us try 7/8. I have a vague feeling this is correct. Alright, so 80. Oh, the math is going to be really annoying though. It is what it is though. Alright, drop the 80. That's easy. That is 302. Is this divisible by 8 though? It doesn't look like it. Let me think. 24, 60. Oh, this is not divisible. But we should continue on regardless. Just to... I don't like these numbers. Let me pause for a moment. Is this a good idea? Yeah, let's just do a rough estimate. So this is close to like 300. This is like 290-ish. This is going to be a positive value. So it's like 300-ish. And then this one is going to be greater than 200, I'm certain. So the result is positive, which means... Okay, this is very rough estimated. But that means that our goalposts are 3/4 and 7/8. So our 0, according to intermediate value theorem, should lie somewhere on the interval from 3/4 to 7/8. Somewhere between those two. I guess that's a good thing, but we gotta find the right fractions for that one. Unfortunately, my fraction work isn't that good. This is gonna be 6/8. What's between here and here? Nothing good, so it must be like a 16? 7/16, really? I really hope it's not 7/16. Okay. But unfortunately, we're gonna have to try that out. 7/16. I think that's between these two, right? 7. No. What am I saying? That's. What am I even saying? That's definitely not right. Hold on. So this one, if you double that one, is 12/16. Double this one is 14/16. Yeah, what am I saying? Like 13/16 is correct. Is between those two. So 7/16 is definitely not between those two. Assuming I've done all the math correctly up to this point, which, you know, it could be dubious. Yeah, these values are super close. I have a vague feeling that I may have screwed something up. Well, let me think though. Let me think for a moment. We don't have a 13. Yeah, these numbers are tremendously close. So 16 is the wrong way to go. If we pick 10... 7/10? Really? Is that a possible situation. Let me think. 30, 28. No, this is lesser than 3/4. So not 7 over 10. 70, 72. Not 9 over 10. That's... This is actually a little difficult. And again, I really hope I didn't screw up something in the way beginning. But it's entirely possible, of course. I'll have to check the synthetic division placement. This is 3, 2, 1, 0. Okay, that's correct. Well, let me check this one again. 240 minus 18 is 230. Yeah, that's correct. This is correct. Okay, so there's no factor by grouping. Yeah, I was really hoping I made a mistake like that, but we do have a positive 0. 3/4 produced a... I better check this, because I'm pretty sure I could easily screw this part up. 20 times 3 is 60. Summoning that is 292. This is definitely correct. And then multiplying that one is 73. Okay, 73 times 3 is indeed 21.9. Yes, summoning those ones is 2. Oh, this is where I screwed up. This is not 242. That is 252. Which means what? Is this divisible by 4? Please tell me it is. Yes, it is. It is 63. 63 times 3. 189. Oh, thank goodness. Okay. So I screwed up. Okay, good. That means that this work was unnecessary and this part was unnecessary. Because I screwed up the math. This is not 180. This is 189. Which means this is 0. Which means this is a 0. Which means x minus 3/4 is a factor. Which means this is the remainder. What do you know? And everything here is probably divisible by 4. So I'm going to factor out the 4 immediately. So that becomes 20. This becomes 73. That becomes that one. Yeah, let's recycle our work, right? There's no need to... Oh, no, I'm sorry. This is not... this one divided by 4 is 63. Yes. We started with cubic. We factored out exponent 1, so this should be x squared. Yes. Don't magically change the signs like what I'm doing. There it is. We'll distribute the 4 to those two, thereby getting... I'll probably put the x. Okay, so that's done, and then this one is honestly kind of atrocious. Is this factorizable? It is a quadratic, but looking at how small this number is, and then looking at how big those ones, this is probably not factorizable, because this is plus, this is plus. So if this is hypothetically factorizable, then you'd have 2 real positive factors. No, there'll be negative solutions. Oh, okay, never mind. We have to check this. All right, let me check. Using discriminant test, we're going to have 73 squared minus 4 times A times C. And by doing this rough estimation, we have 80 times 60-ish, which should be greater than 73 times 73. So I think there are no real solutions, but I don't trust my quick math. So let me consult the old calculator. We have 73 squared minus 4 times 20 times 63. Oh no, it's a positive answer. Which means, is this a perfect square? Oh, it is a perfect square. Oh goodness. Alright, So this one will yield a square root of, what was it? 289. And that one becomes positive 17, so plus or minus 17. Ooh, okay. So that's the significance of discriminant test. Okay, so we can proceed using typical factoring methods. Use your favorite one. 20 and 1, 2 and 10, 4 and 5. 63, factors of those ones, 63 and 1, 3, 21, 7 and 9. We're missing something, aren't we? Yeah, 7 and 9, that's it. Alright. So which of those combos can potentially produce a positive 73? Both are positive. Both are same signs. Everything summates to be positive 73 in the middle terms. Well, let's see. That gives us 35, and then this one gives us 36. Right? That gives us 70. Oh, that's so close. 71. Okay, so we're very close. You almost never pick the extreme values, of course. Probably not that one. Let's try this one times this one times that. 70 and 18. No, that's worse. Interesting. 60 plus 21 is 81. That's not quite right. No. 8. No, we already tried that. What am I saying? I'm goofing up. We already tried that one. It has to be this one. That is a 30 and a 42. No, also not quite right. Wait, what? That's not quite right. Interesting. Let me think. Let me pause for a moment. I'm not seeing it. Well, I think I already did this one right. 70, 18. Yeah, already did that. Okay, let's be a little more methodical about this. Let me start with this one. Can we possibly produce a 63 starting from this one? That's 83. No. That's 81. No. That's already overboard. That's 100. So definitely not the 20 and a 1. Is this possible? That's really bad. 30 and 42. No. And then all the way 200. No, that's too much. 70 and 18. Nope. And 90 and 14. No. So definitely not this one. So maybe this. Either of these two multiplied to 63 is already too much. So no. 15 and 84. No. That's not looking good. Wait, didn't I already check this one? 45. Oh, I didn't do it the other way around. Silly me. Alright, well, 5 times 9 is 45, and then 4 times 7 is 28. Summating is indeed 73. What do you know? I should have just carried on with the, what's this called? Discriminant of the quadratic equation. Yeah, I should have just continued with quadratic equation. What was I doing? What am I doing? So, copy paste this particular factor, the first one that we found. This is a quadratic, so use your favorite quadratic factoring algorithm. It must be a 5x and a 4x. The 4 has to be multiplied to the 7, so here goes the 7, and then the 5 has to be multiplied to the 9. Both signs are the same, both are positive. Yes. This is fully factored form. Let's do a real quick test check. This is 21 times 9 is 189 negative. Yeah. 4 times 4 times 5 is 20. 20 times 40 is 80. So 80x squared. Okay, yeah, seems legit. Quick test. Not exactly a robust test, but good enough. This is probably correct. Fully factored form. So we are done. with that problem. Yes, that was super tedious. Scratch that off. Next problem up, we're going to have the x power 10 minus 1. I think this is a fairly classic type of problem. You might see something like this. You might see like x power 20 or x power 30 even. So this one is a difference of perfect square number 1 and perfect square number 2. So use your favorite factoring by perfect square method. I mean, difference of two squares. So square root of that is this, and then square root of just the 1 is here. And you just copy paste it, alternating the sign only. That's the algorithm. Again, I'm not talking about the mechanics of why that happens. That was last time. So here we go. There's that one. The question is, can we factorize this any farther? This one... This one actually has a real solution. This one also has a real solution. So can we factorize this even more? Yes and no. Again, it depends if you want to have rational or if you care about rational versus irrational coefficients. If you care about having rational coefficients for your end product, then you stop here. Oh wait, no, we actually have a 0 here. Just kidding. This is a 0 because if you plug in 1 minus 1, that's a 0. Okay. Just kidding. Disregard what I said in the last 5 seconds or so. Okay. So we have the 5x minus a 1. Right. According to Descartes' rule of sign, you're changing from positive to negative. So one sign change, and because this is an odd exponent, you are guaranteed one solution, one real solution. Because again, cubics or odd-powered exponents are going like something like this. You have to cross the x-axis at some point. All right, so this one, like I said, if you can see it, you plug in positive 1, then that produces 0. So because of remainder factor theorem, this is a 0, which means x minus 1 is a factor of this junk. So we can do synthetic division to get the quotient. Let's do that. So again, this one is positive 1. Don't do this setup, please. Or what am I saying? Don't do this setup. This is wrong because this is exponent 5 jumping to exponent 0. We must account for all the invisible terms, meaning we have x power 5 plus 0x4. Doesn't matter if you put plus or minus because it's just 0. And then plus 0x cubed plus 0x squared plus 0x minus 1. So we have four zeros to account for. There'll be no vor here. Never ever. It's disgusting. We have 4 zeros. 1, 2, 3, 4. And then we have minus 1. Alright, here we go. Summate, product, summate, product, summate, product. It's going to be the same thing. Why even bother wasting time? It's a positive 1. Summate is 0. What do you know? Which means that is a 0, which confirms that this is indeed a factor. Don't forget the rest of this riffraff. This is what? Degree 5 divided by degree 1, so we have degree 4 for this one. So degree 4, degree 3, degree 2, degree 1, degree 0. Alright. And I think that's all the real factors we have for that scenario. If you use Descartes' rule of sign, no sign changes, so we have no positive real ones. Do we have 0 solutions, though? I mean, do we have negative solutions? Well, let's do a quick check. Negative 1. Only using negative 1 because this is only 1 and only 1. So there are no other possible candidates that are rational. So that's this. Alright. Yep. 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 because we have a non-zero remainder, this is not a 0. Trying 1 again will not work. As specified before, so this one should be fully factored, so we have this one. Should be good, so we can successfully factorize this into that. This one is not a familiar situation, because this is neither a perfect square nor a cube. That's interesting. Okay, well, fx minus 1 times all that nonsense. You know what? I'm too lazy. Let me just move things over. The perks of the digital medium, yes? So let us take this fully factored form of the first thing, put it there, and let's take that copy. You know, I have not been using the copy paste function. Here we go. Oh, you know what? We actually have a 0 right here. So if you have a x power 5 plus 1 and you force it to be 0, we can actually get x is equal to negative 1. Well, we do have a 0, so this one also needs to be factored. This is should be fully factored form. This one is not fully factored. That is a 0. This must be a factor of this. Alright, so let us carry on with that one. Don't forget though, we have invisible terms. It's going to be pretty much the copy paste version of this one. So we're going to have we should have 4 zeros sandwiched between x power 5 and x power 0. Yes, because 4, 3, 2, 1, yeah, 4 zeros. So let's do the long division. Okay, this is the 0. We're going to use this to populate here. So 1, 1, 0, 2, 0, 3, 0, 4 zeros, and then positive 1. Alright, let's execute the standard algorithm. Wait a minute, did I? Yeah, I did. Well, that's what I get for just doing things mindlessly. 1. This is going to alternate, isn't it? Yeah, negative 1, positive 1, 1, negative 1, 0. Okay, that's looking good. Yeah, this thing looks really annoying. Let me think about this for a moment, real quick. This is a negative solution. There's no real positive solution. Yeah, that's correct. Alright, what does that mean for us? It means we should probably run one more synthetic division test. Probably run on this one more time. Let me just check it real quick. I don't think it's going to work, but a paranoid part of me is worried. Yeah, it's looking bad. It steamrolls. Snowballs, yeah. Yep, okay. So there should be no more real zeros for this scenario. So therefore, once we factor this one, this is fully factored, that's fully factored. I hope this one is not factored. We just factorized this one into this times that junk. Yeah, make sure you remember how to translate that. Remember, that is downticked x power 5, downticking it by 1 exponent. So x power 4 minus x cubed plus x squared minus x and then lastly plus 1. Yes. Being the lazy person that I am, I'm going to take this one and put it right here. There you go. So that is the fully factored form of the 5x plus 1, I hope. We're going to take that. Again, perks of the digital medium. I don't have to rewrite this. I'm just going to steal it, put it right here. Why is my spacing so bad? Take that portion here and plant it. Okay, it's like barely enough space. You know, that's good enough. let me move things and then I'll make final comments. Everything's too close for comfort. Let's give some personal space. Okay. So here should be the fully factored form. I don't see anything else that's... I don't recognize anything else that's immediately factorizable to my eyes. So I think that's it. But for... Again, I'm feeling slightly paranoid. I'm going to check it by running it into the calculator real quick. So 10x to the power of 10 minus 1. Let's see if this is factorizable according to this calculator. Yeah, they only have 2 real roots. I think they got the same. Yeah, they got the same thing. Okay, good. That gives me great confidence. This is the most we can do, according to me, according to the calculator. Alright. Actually, that was a lot longer than I thought. I thought this would be a lot sooner. That's okay. So we're finished with that one. I do want to introduce another type of problem that's very similar, and it's the ambiguous situation. So for example, we have x power 6 minus 1. So this one is the slightly annoying situation. And let me tell you why it's annoying. It's annoying because there are 2 ways to interpret this. You can interpret this as a difference of 2 squares, or a difference of 2 cubes. So the question becomes, which one do you use? In which order will you try to factorize this using special factors? Will you attempt to do it as a difference of 2 squares, or a difference of 2 cubes? Or does it even matter? And let's just see what happens in both scenarios. So this one right here, let me think about how I want to express this. Yeah, let's just do it both. Let's just use the difference of 2 squares approach first, because again, this is just for exploratory purposes. So if you decide to treat this as a difference of 2 squares, then we're going to follow standard algorithm for this. Take the square root of that is going to be x cubed. Because again, when you multiply these, you just add exponents. Factors down, that's just 1, 1. This is a difference of 2 squares, so you have to put minus and plus. Okay, so that looks good because this is a difference of 2 cubes and this is a sum of 2 cubes, which are further factorizable. But let us see what happens if we had done the alt strat. Like, what if you try to factorize this thing, the starting problem, as a difference of 2 cubes, right? So let me jot that down. So diff of 2 squares. Why is my writing so atrocious? Imagine having legibility. Difference of 2 squares. And then this is a difference of 2 cubes treatment. Like, the question is one preferable to the other one, or are they the same thing? If memory serves me correctly, one of them is better. I think this is the better one. I think treating as a difference of 2 cubes leads you to kind of a bad situation. I think. So again, treating this as a difference of 2 cubes, then the cubic root of that one, you just divide the exponent by 3. And then you find the cubic root of -1. This is -1, easy. Following standard algorithm, it's going to be this one squared gets you the first term. First term times second term, flip the sign to get to this one. Lastly, this one squared takes you to here. Alright, so we do have something here at least. We have a difference of 2 squares, which is not a coincidence, right? Here we treat it as a difference of 2 squares first, thereby getting a difference of 2 cubes and a sum of 2 cubes. But treating it as a difference of 2 cubes, we can get a difference of 2 squares. But this is, what is this, right? I don't think this is factorizable. But this is some sort of quadratic looking thing because this is twice that, and this is exponent 0. So I think this fails the discriminant test, but just to be certain, this is going to be 1 squared minus 4ac. This is a, this is c, times 1. And we do indeed get a negative discriminant, which means this has no real solutions, which means this is not factorizable with real coefficients. So thus, the only thing you can factor is this leftover junk right there. Difference of 2 squares, that's easy. X plus 1, x minus 1. Fairly straightforward. If you memorized it. This one, nothing to do. So this is one form. Let's check the other side. This is a difference of 2 cubes, and that's a difference of 2. That's a sum of 2 cubes. So this one has its own factoring algorithm. Again, cubic root of that. Cubic root of that. This one squared takes you to the first term. First times second gives you here with the flip sign. This one squared takes you here. There you go. Sum of 2 cubes, same thing, same overall strat. Cubic root. Cubic root. This one squared takes you here. This one times this one, flip the sign, get you there. 1 squared is 1. There it is. So that's fairly interesting. This one we have 4 distinct factors. This one we only have 3 distinct factors. So what just happened, right? Something seems wrong. So we have this one here. Let's check the bookkeeping. This one is present there. So what the heck is this? Like this one and this one is supposed to be this one, right? Like, is that correct? Seems that way, right? But I don't think we have a factoring algorithm for here. So I think it's always preferable if you have an ambiguous situation and you're trying to distinguish between using a difference of 2 squares versus a difference of 2 cubes. I think you always do difference of 2 squares first. I think that's the strat, because again, this one here, by checking the discriminant test, we can't factorize this using real numbers. It leads to a bunkered situation. Why is that? I am not exactly sure. My mathematics, unfortunately, isn't strong enough to justify why that is. But for the sake of further exploration, let us distribute this 3 by 3. So let's distribute this 3 thing here to those 3 things there, just to see if it ends up becoming that thing. I don't think it does. So let's see, this one times this one. Make sure you have some sort of semblance of order. Always, always, always. This one times this one. So we're finished with the first. Doing the second one times that one. This one times that one. This one times the last one. Done with that one. Now 1 times each of those. Just copy paste this whole thing since it's just times 1. Interesting. Summating. Those ones cancel. Those 2 cancel. This one's still here. Those ones cancel. That one's still here. What do you know? It's that one right here. Yeah, as it should be, right? It's supposed to be congruent. Do we have an algorithm for factorizing this? I think we do. I think there is technically a factoring algorithm to do it. And I guess you have to split this one. Oh, let me think off the top of my head. I don't have an immediate algorithm for this one. What do we need to do for that? I don't think there's a good algorithm. Again, off the top of my head, because of the way this distribution works, this is a 3 by 3 distribution, and we end up with 9 terms in total. So I think technically you would need to have you need to have a good way of splitting this into 9 scenarios, into 9 terms. Yeah, you have to split it into 9 terms. So I don't think there's a good algorithm to factorize this. So, long story short, if you're given an ambiguous situation and you're trying to determine, should I use difference of two squares strat or difference of two cubes? Use the difference of two squares. Otherwise, you're going to get this junk right here. Okay, but this problem's done. It wasn't even part of the original plan, but that's okay. Alright, so we have a few more problems to do with just x's. I have this triple star problem, which looks atrocious. We have a super tedious problem, and then we have a better looking problem. Let's do the easy one first. So of the three that remain, this is the easiest looking one. So we have 12x cubed minus 26x squared and plus 16x. Okay. We can kind of see this is an even number, even number, even number. Has x factor. So everything you can slap on the parentheticals and factor something from all three terms. Right? This is 2 times 2 times 3. This is 2 times 13. So the most we can factor out is just 2 from all terms and x power 1. So we can factor out 2 and an x power 1. So 12 divided by 2 is 6. Down take the exponent by 1. No, that's a negative 13. Down take the exponent by 1. Divide by 2 and x, so we have 8. Okay. Thereby revealing a quadratic. Half of this is 3. Half of that is 4. It's a 12. This is not a perfect square. That's okay. Factors of 6. 3 and 2. Factors of 8. Yeah, that's it. Which of those combos can potentially produce a negative 13? This does not look like a good number. Oh, is that it? Oh, wait. Is it really it? No, they're the same signs and both of them are negative, right? Yeah, that's not quite it, unfortunately. So what else is there? 12 and 4. No ways makes 13. Let me use the discriminant test at this point. I think this is not factorizable, but we need to check using discriminant test. Squaring the negative 13 gets us negative 69. Nice. And then we have minus 4 times those two. Yeah, that does not look like a positive scenario. I don't think so, because this is just, again, this is 13 times 13, and then this is more than 13 times more than 13, I think. Right. Let me split this. This is going to be 2 times 6 times 2 times 8, which is 12 times 16, which I'm very certain is greater than 13 times 13. Right? That sounds dubious. I don't trust myself anymore. Let's do 12 times 16. That's 192, which is greater than 169. So therefore, the discriminant test reports back a negative. Therefore, no real solutions. Therefore, this is not nicely factorizable. So we're done. That's it. That's funky. So we start out with this one. We could only factor 2x from all three terms. Once we reach here, this is a not factorizable with real coefficients situation. So we'll stop here for this problem. Well, that was easy. Alright, so I guess I've delayed it enough. There's this huge tedious problem. But let us solidify our approaches for doing these type of problems. So we have 80, a whopping 80 x to the power of 5. And then we have minus 136 x4 minus 160 x cubed. Look how huge those numbers are. That's a yikes. And then minus 10x squared plus 17x plus 20. Gorgeous. It's gonna be bad. What are the factors of you see how this is a prime number? Because this is a prime number, you can't factor something from all these because this one has no 17s and this one for sure has no 17. Oh, this one for sure has no 17. So, because nothing else has a 17 and this is the only thing it has going for this coefficient, you cannot factor something from all terms. So that's pretty bad, right? So do we just resort to long division with the candidates of 20 divided by candidates of 80? I don't think so. Let me see something. Can we factor by grouping, right? Because we have 1, 2, 3, 1, 2, 3. So we have a total of 6 terms, even amount of 6 terms. So I hope this is factored by grouping. Let me see. Factors of 80. 2 times 2 times 2 times 10, which is 2 times 5. What are the factors of this one? I hope there's a 17. If there's a 17 in here, we could probably factor by grouping. But if there's no 17 here, then we cannot factor by grouping. I don't think. So do we have a 17 here? What is that? It's 7 times what gives us a 6 ending? 8? Wait, is it actually? Hold on. That's not seem right. Is it really 8? Let me see. 80 plus 56. Hey, oh, okay. Good. Good to know. Wait, what did I say? 8 times. Too bad there's no one in chat to tell me this. It's 8 times, what did I say? 17. Yeah, 17. Yeah. Suspicion is confirmed. Yes. Okay, so this is a prime candidate for factoring by grouping. This is probably 8 times something. 8 times 20. Yeah, 8 times 20. Oh, thank goodness. Okay. Yeah, you see how this is a 5, which matches a 5 and... Wait a minute. Oh, no, this is a 10. Yeah, this is a 10 if you factor out an 8, which matches a 10 here. Perfect. This is 8. 17 matches. This is an 8. The 20 matches. Okay, so this is a factoring by grouping problem. Oh, thank goodness. All right. So what that means for us is we can slap on the parentheses around here. And remember how to do it for this one. Don't just put it like this because you're saying that's multiplication. It is not. So you have to put a plus. If you put a plus in front of the parentheticals, you are always correct. All right. So from these ones, all of those, we're going to factor out an 8x cubed. 8x cubed from the first red grouping, thereby getting 10x squared minus 17x1 minus 20. Which, what do you know? Wait, what's the sign? Oh, okay, never mind. We just need to factor -1. Okay, thank goodness. So from those, we could factor out -1 from each of those 3 terms. So factor out -1, thereby getting 10x squared plus 17x plus... No, everything gets flipped with signs. So we're factoring out -1, so the negative becomes positive, and the positives become negative. Yeah, okay. So negative 17x. Negative 20. Alright. Oh, I just drank a seed. Well, from a lemon. Wonderful. That's okay. I'll just pass through the digestive tract as expected of seeds, right? Okay. So if you slap on the old brackets, we can make note that this entire chunk here is exactly the same as this chunk there. So term number 1 has a common factor to term number 2. So we can factor out the chunky factor. Yeah, so bring that out of the brackets. Thereby getting 10x squared minus 17x minus 20 in parentheticals, of course, and then brackets 8x cubed minus 1. Close. Alright, so take a survey at this point. This is a difference of two cubes. Difference of cube number 1, cube number 2. So this has its own factoring algorithm. We're going to deal with this momentarily. This one is a quadratic. Is it factorizable? Ooh, this is a negative. Because this is a negative, this is going to be factorizable. But is it nicely factorizable? Let me see. 10, 1, 2, and 5. Factors of 20. 21, 2, 10, 4, 5. Can we produce a negative 17? Can we? No, that's bad. 20 and 10, no. 25 and 8, yes! Okay, so this is factorizable. From these two combos, always the intermediates, right? Okay, so the 5x and the 2x. The 5 has to be multiplied to the 5, and the 2 has to be multiplied to the 4. Two signs are different, the larger the 2 is negative. Yes. Okay. So that's fully factored form for the quadratic. This is the difference of two cubes. So again, the algorithm, don't forget the algorithm, take the cubic root of that is 2x, cubic root of that, negative 1. Square that to begin populating. This one times this one, sign flip takes you here. Square that to get third term. Okay, that looks good. We're going to take that, slam dunk it right here. This is good. This is exponent 1, that's good. This is exponent 1, that's good. That's good. This one is, again, in my experience, is never factorizable. But if you're paranoid, you could always check using discriminant test. So b squared minus 4ac is a negative value. So this one has no real factors. Which means we should be good to go. This is good. Alright, cool. So again, that was a factoring by grouping problem. Given large coefficients, you do need to do a test of you need to do a breakdown of the factors just to see if you have match, and then you have to play match game. Do we have any of these factors matching those factors? In this situation, we did. So, lucky us. And then final problem for this particular set, I put 3 stars next to it. So I think there's a gimmick to this problem. So we have x power 6 and then 12x4 plus 48x squared, lastly minus 72. We have 4 terms right here. 4 terms right there. So the question is, what do we do for this scenario? So just a quick evaluation by looking at the situation. We have exponent 6 minus 2 minus 2 minus 2, right? That feels like maybe a pattern. So we might be tempted to check factor by grouping first. Maybe grouping those two and those two, right? But check the coefficients. This is coefficient 1. This is coefficient 12. So this needs to be a 12 and this needs to be a 1 if you successfully can factor from those two. So let's break down 48 into 6 times 8, which is 2 times 2 times 2 times 2 times 3. That is 8 times 6, yes. Break down this one is just 8 times 9, which is 2 times 2 times 2 times 9. Alright, unfortunate, wait, this looks like it could match, right? This is 12, that is a 12, so we need to bring out a 3 times 2, 3 times 2. That does not match, so check this out. So again, if you're hypothesizing that maybe you can factor by grouping, if you group those two, then you will get x power 4 quantity x squared minus 12. This one, in order to try to match this as much as possible, you need to keep a 12 inside, so you have to factor out 6. So if you factor out the 6, you're left with an 8, a very unpleasant 8x squared. But here you have the 12 that you desire. So unfortunately, this thing here does not match that thing there. So factoring by grouping most directly has failed us. So that is rather unfortunate. So how do we proceed with this one? Well, this is kind of a cheese problem, honestly. I don't think many teachers will give this out. Maybe if, let's say there are 100 teachers, I think 99 would not give this type of problem. Maybe one might give this problem. But I don't think they'll give it for like a test, for example. But I wrote the problem. I'll just write the answer that it's supposed to be. So the answer is supposed to be x power 2 minus 6 times x power 4 minus 6x squared plus 12. So this is how I designed the problem. I deliberately gave this thing right here, which is squared. So this is technically factorizable. You're just going to get a rational constant. So this is a rational 0. And then this one is non-factorizable, because if you do this one squared, it's going to be 36. And then minus 4ac is minus 48. So this one has no real solutions, which means this one is not nicely factorizable. What ultimately that means is if you try to do the standard procedures of finding candidates of 72 over candidates of 1, you're not going to find any real solutions. So it would fail in this situation. So what are we to do? So I'm going to take this right here, okay? So this one right here, that's the answer. I'm going to hide it right behind me real quick. So we'll save that for later. So basically, I came up with the solution for doing this, but it's kind of annoying, honestly. It works though, but you kind of have to understand ahead of time that this is kind of a cheese problem, and then someone should give you a hint that you can factor this by grouping. So let me show you the method that I wrote down to solve this, to factorize this problem, because again, the standard algorithm will not work. And straightforward factoring by grouping also does not work. So here is the method that I wrote down. There are surely other methods, but I don't know those other methods. So here's what we're going to do. So currently we have 4 terms, and we attempted to factor by grouping, but that has failed. So what we can do is we can try to split terms to make other groups. Alright, remember where I said in the beginning, factoring by grouping, you typically need even amount of terms. There are 4 terms. So if we split this one up into 2 terms, we will get an odd number of 7. No, I'm sorry, what am I saying? We'll get 5 terms, which is not conducive for factor by grouping. So we need to split 2 terms, you understand? So we're going to split the middle one, the 2 middle ones, into 2 terms each, which gives us a grand total of 6 terms. For purposes of factoring by grouping, you never really do anything with those 2, unless it's a weird situation, I think. Alright, so having said that, this one will split off into 2 terms. But the question is, what does it split into? We're not going to play guess and check. Because splitting 12, there are many combinations for 12. For example, you could split negative 12 into negative 1x to the power 4 minus 11x to the power 4. So this one, if you recombine them, takes you back to right here. But that's just one combination, right? Can't you split into negative 2 and negative 10x to the power 4? You see the conundrum here? But that's not the only thing you can do. That's treating them as negative terms. What if this is actually a combination of positive 1x to the power 4 plus negative 13x 4? So as you see, there's an infinite amount of combinations, but you know, some combinations are worse than others. So for sake of efficiency, I'm just going to split this into a x power 4 and negative, no, hold on. Here's what I'm going to do, okay? This is essentially, I'm going to split this negative 12 into a minus 12 and negative 8. Okay? So if those are the coefficients for x power 4, if you recombine them, you get back to negative 12. Alright, so as a disclaimer, if you're a person watching this VOD, you can entirely skip this problem and it will not be a big deal. But if you're interested, just for the sake of exploration, stick around. Okay, so this one again, I'm arbitrarily splitting it using an unknown value. So that way, I'm not committing to any sort of combination. So this one, again, I'm going to split this negative 12 coefficient into a minus 12 as one coefficient. And then the other coefficient will be plus a x power 4. So again, the reason, if you redistribute this and you add this one up, oh, this has to be subtraction. Just kidding. Almost screwed up. So that's why you always double check. There you go. Because if you distribute this, you get positive ax power 4, which if you combine it with that one, will thereby produce 0. Those two will cancel out, and then leaving you with just negative 12x power 4, which is that one. Okay. Let me try to document this as neatly as possible. So again, the goal is to split this one to here and then this one to there, because maybe we suspect factoring by grouping, or someone told you right off the bat you can solve this by factoring by grouping. So that's the disclaimer, right? Otherwise, how would you know to use factoring by grouping? I don't think most people would attempt to do so. Alright, so keep this one as is. We are also going to split up this one in particular using the same style. 48, we can split it into b plus 48 and then minus b for the coefficients of x squared. So again, if you distribute this to the x squared, the negative bx squared will cancel with positive bx squared. So that is the idea. Let me delete this arrow real quick. Let me just toss this over. Again, this one, we're going to split it into positive b plus 48. That's the x squared. And then, of course, we have the minus bx squared. This doesn't look like a b. Let me change it more to b-like. There it is. And then we're going to have a minus bx squared right there. So again, if you distribute this to this one, you get positive bx squared, which will negate with that one if you summate those. Alright, final thing, copy paste the negative 72. So what have we done? We split this negative 12 x power 4 into this term and that term. And then we split the 48x squared into this term and that term. Because the goal is we want to have something here that will match this one. I'm sorry, we want this. So there are 3 terms now on one side. There's 3 for this group, and then there'll be, let me use a different color. There are now 3, well, that's a really bad color. I'm sorry. We have 3 terms right here that we are potentially trying to group, and then we have 3, that's also bad color. We have 3 terms over there which we're attempting to group. The idea behind factoring by grouping is you want to have similar factors across both groups. So in other words, group orange has to have common factors with group purple. And by doing this awkward splitting situation, splitting this one and splitting that one, we are attempting to force the matching across those 2 groups. Okay? And we're going to use algebraic manipulation to try to force the situation. Okay. But, okay, well, more detailed. But let us execute the plan. So this one right here, because this has a 1 coefficient, then this one is not factorizable, and nor is that one factorizable. We can only factor x squared from each of those 3 terms. So let us do that. I'm going to keep the orange parentheticals just to keep things visually clear, I hope. So this is going to be x power 4 plus, in parentheses, a minus 12. Again, I like parentheticals because it kind of keeps things clear where they're coming from. So this one I'll keep in parentheticals. You don't have to, though. Alright. So that's the first group factorization. So again, we want these things here to essentially be identical to whatever we have inside there. Alright, so this one, unfortunately, it does have an A in the front. Alright. So that looks kind of bad, but what do we want? We want this coefficient to eventually match this one. So that tells us that we need to factor a negative A from those three terms. So factoring out the A from the purple grouping, so thereby getting, what are we going to get? We're going to get positive x power 4, and then positive b over a, x squared, and then we're going to get negative, or I'm sorry, positive 72 over a. Well, that's kind of awkward. Alright. And now all you have to do is play the lineup game, and thankfully we only have two variables. So remember, we're trying to force orange group to perfectly match purple group. So we're just going to manually set them to be so. This one coefficient already matches this one coefficient. So these two are successfully matched. So can we match this one to this one? So we're just going to force the match first. So we're trying to make this coefficient match this coefficient. Otherwise, we can't factor by grouping. So we're going to force the equality right there. There it is. So unfortunately, this is one equation, two unknowns. So we have a second equation, which thankfully we can match this one with this one. If we can get them to match, then we can factor by grouping. So b plus 48 is equal to this junk, hopefully. So we have equation number 1, and then we have equation number 2. We can set up a system of equations and thereby solving for A and solving for B. And I think it's doable. So what I'm gonna do? What is the easiest way to do this? I'm gonna solve for 1 over A. So solving for 1 over A, we're gonna get A minus 12 over B is equal to 1 over A. And then we're going to divide 72 from right hand side and left hand side. Oh wait, that's not a good solution. I'm sorry. Let me backtrack just a little bit. The idea is correct, but the execution is wrong. This one kind of is awful. Let me just solve for B. Let's keep it simple. Solving for B by multiplying A to both sides, we're going to get A squared minus 12A is equal to B. And we're just going to subtract 48 from both sides. So B is equal to 72 over A minus 48. So therefore, this is equal to 72 over A minus 48. So this just has A terms, and this just has A terms. Perfect. So we can combine those two, thereby generating A squared minus 12A is equal to 72 over A minus 48. What a pain. This is looking like a polynomial where we need to multiply both sides by A, assuming A is not 0. So A cubed minus 12A squared equals 72 minus 48A. Wow. What does this mean? This means that we have a polynomial problem inside this polynomial problem. We start off with this. We're hypothesizing that we can factor by grouping. We're forcing the groupings to match. In order for the groupings to match, this thing has to be consistent. So we have to be able to solve for A. So A cubed, let's move everything to one side. So A cubed minus 12A squared plus 48A minus 72 is equal to 0. So again, in order for, remember what happened. So here we're force matching the coefficients. We're trying to force this one to match this, and simultaneously forcing this one to match that one. If we can match them, then we can factor by grouping. If we cannot match them, because there's no solution to this, then we have no way to factor by grouping, and this whole thing is for naught. Alright, so do we have a solution for this? This takes us now to a standard problem, right? This is just a cubic polynomial. Let's use Descartes' rule of sign first. We're guaranteed one answer, at least, one real solution. So this is changing from positive to negative. That's 2 changes, that's 3 changes, which means we are guaranteed to have one positive real solution, which means we can probably do it, right? Can we factor by grouping this one? Well, that would be so obnoxious. Let me see. 1 and negative 12. And then, no, we can't. This is not quite. Not quite. Okay, so we need to do standard factoring rules for this one. So let's do synthetic division. But what are the candidates of 72, right? So we have 1 and 72. Listing all factors of 72. It's just 8 times 9, which is there. So next up candidate is 2 and 36. Yes. Next one up is 3 times 24. Next up is 4 times 18. Next up, there's no 5, there's a 6, so 6 times 12. We probably don't need to list all these factors, honestly. Or what did I say? 6 times 12. But just for sake of completion, I'm going to list them all out. Next up, no 7s, there's an 8 times a 9, yeah, that's it. Plus or minus. Because this just has coefficient 1, so it's all over 1. Alright. So which of those candidates should work out? Again, we're guaranteed one positive real solution, and I don't think picking 1 is a good idea. So let's pick 2 or 3. Let's pick 3. Let's see how that works for the synthetic division. As a candidate for 0, we're going to pick positive 3. Make sure the coefficients are present. This is 3, 2, 1, 0. Yes. All inputs are there. Drop this one. Multiply. Sum. Multiply. Sum. Multiply. Oh, we're so close. We have a remainder of 9, negative 9. So that's very close. Which means our answer is somewhere within close to 3, maybe 4, right? Let's test 4. I'm getting awfully hungry. So let's drop this. 32 summation. Wait, oh, and that's negative. Okay, so summation is positive 16. Yes. Multiplying that is 64. Nintendo 64. Okay, well, that gives us a negative 8, which is closer. So upticking from 3 to 4 gets us slightly closer. So do we pick 6 or do we pick 8? Because there's no 5. Okay, I guess if there was a 5, we'd get closer. So probably a 6. Let's try 6. It better work. Okay, we're attempting to solve for A. If we have a solution for A, which according to Descartes' rule of sign, there should be a value for A, then there is a way to factor by grouping. Alright, so trying 6 now. This had better work. Copy paste the coefficients. Standard procedures at this point. Here we go. Yep. Yes. Negative 36. Okay. Looking kind of okay. Okay, good. 72. Thank goodness. Makes a 0. So, thus, a is equal to 6 is one possible solution. But remember, Descartes' rule of sign reports that we can have up to 1, 2, 3 real solutions. So we check one more positive solution. Remember, this is a quadratic because we downticked from exponent 3 to exponent 2. So all we need to do is discriminant test for this one. So x squared minus 6x. You don't need to write this, but I'm going to write this just to tell you where the numbers are coming from. So discriminant test is going to be b squared minus 4ac. So minus 48. That's a negative value, so that means we have no other real solution. This is the only value that's real for a that will satisfy this one. So a must be equal to 6. Which means that there is a way to force this one to match this one if a is 6. And this one will also match this one if we force a to be 6. So, perfect. If we force a to be 6, then 72 divided by 6 is 6. What am I saying? 12. It's just 12. So b plus 48 has to be 12. So therefore, b is equal to negative 36. Okay. So a is equal to 6, and then b is equal to negative 36. So those ones, if a is 6 and b is negative 36, then this factor will match that factor. Then we can factor by grouping. Wonderful. So let us populate the chart. So again, we figured that a is 6. So we're going to get, let's just start filling this. Oh, this is such a mess. Okay, well technically we don't need this work anymore. We just need to know that a is 6 and b a is 6 and b is negative 36 in order for the factoring by grouping to work out. So let me shove this to the bottom. So all that work was just to determine if it was feasible to do factoring by grouping. And now that we've found the values, we can just do it. So again, a is equal to 6. So 6 minus 12 is negative 6. Then b is negative 36. Negative 36 plus that is 12. Yes. Again, we determined a is 6. Negative 36 over 6 is negative 6. Looking good. Of course it should, because we already did the math. So that one is going to be 12. Yep, so this group here perfectly matches that group there, right? So we can slap on the old brackets. We can factor chunk number 1. Let me rephrase it. We have term number 1 here, and we have term number 1 there. So from those two terms, we can factor out this particular factor chunk. Bring it out to the front. So thereby getting x power 4 minus 6x squared plus 12. Parenthetical, and then x squared minus 6 left over in the brackets. There's nothing to be done here. This is a difference of 2 squares. If you really want to treat it that way, you can. If you don't mind having irrational numbers. Okay, but let's make sure that matches the original answer. Oh, I think I deleted it. Oh no. Did I? Okay, well I wrote it down somewhere else. Let me see real quick, just to check my answers. The answer that I had written elsewhere was x squared minus 6 times quantity x power 4 minus 6x squared plus 12. Does that match? Yep. And yep. Okay, good. That's correct. What a journey, right? Okay. So again, we start with this thing. Immediately, right off the bat, we could not see factoring by grouping as possible, and then another factoring method has failed. If nobody told me anything else, I'd just stop there. I'd just give up and not factor it, because it's not worth the time. But because I designed a problem, and then now I'm telling you that it is factorizable by grouping, then you have to force the groups. The group of 4 did not work, so you have to split it into groups of 6 total. And then we force the matches if possible. And since the matching was possible, then we could factor by grouping. Because all this work here was to justify that. And we are done with probably the most difficult problem of the set. Wonderful. But there's a certain artificiality in it, right? Yeah. That is it for that one. Let me think if I want to go on. It is kind of late, but I'm feeling pretty good. I was thinking about going on to factoring other stuff with multiple, with not only x, but also like x, y, for example. I think, let's do, it turns out there are 2 more problems here with just x's. So let's finish them. Let's keep the good form, right? So we have 6. Once I get this done, I'm gonna I was gonna say eat a cookie, because I deserve it. But it's kind of bad for me. Sugar at this hour? I should have some semblance of health concerns, right? Alright, so we have 6x4, we have that one, we have 82x squared, we have minus 155x, and plus 50. Oh, okay, take a quick evaluation. Is this a nicely factorizable situation? So you check all terms first, right? This is 2 times 3. Did I do this problem? And I just did not cross this out. Okay, well, if I did this problem, you could just skip it on the VOD. That's okay. This is 53. I don't think it's factorizable, so we can't factor something from all terms, unfortunately. Yeah, because I think this is, even disregarding this one, this is just going to be 5 times 31? Yeah, see, this 31 doesn't share anything with the 6, and the 5 doesn't share anything with the 6. So right off the bat, because these two are in conflict, you can't factor something from all 5 terms. Right? Okay, well, so factoring from all 5 terms is a no-go. Is it possible to factor by grouping? Well, from a quick evaluation, this is 1, 2, 3, 4, 5. We have 5 terms, so as it's written, there's no good factor by grouping. But can we force the factor by grouping? Maybe. Maybe. Let me see the factors of this one. I think this is the biggest obstacle, because this one doesn't have any factors other than itself. This is prime. Can we split this one? Let's see real quick. I'm not going to actually do it all the way, however. But hypothetically, we can split that into, same strat as before, a plus 82 for one term, and then we can have a minus a x squared for the second part. So again, if you distribute those back out, you can cancel those two. Alright, so is it possible, right? So this one right here is going to be negative 155x. This is plus 50. I don't think so, because again, the biggest problem with attempting to force the factor by grouping is this is a very poor 53, which there's no 53 here. So I don't think I'll continue with the factoring by grouping strat. So again, if this one had instead been like a 53 times a 5, for example, then maybe this forcing the strat might work. But as it's written, I don't think it's a good idea. So I'm going to leave it as a typical factoring problem. So let us hope that this works. That's a typical factoring problem. Alright, so factors of 6, 6 and 1, 3 and 2. Factors of 50. That's a real doozy. 2, 25. I should probably write up the factors, right? Fully factored form. So 2 times 5, times 5. Oh, that's it. That's not too many right there. So the next number up is a 5. So 5 times 10. I think that's it. 25 times 2. Yeah. Easy enough. All over those ones. 2, 3, and 6. Plus or minus. Alright. So hopefully this goes well enough. I hope that this is a typical problem and not some sort of wacko problem. Alright. Let's make sure all terms are present and accounted for. 4, 3, 2, 1, 0. Perfect. Copy paste the coefficients. As you see, the numbers are kind of snowballing just a little bit. Not really. They're kind of close. All right, they're okay. They're not too snowbally. When I say snowball, I mean like you have a 1, 1, 2, and then you have like a 100 or something like that. That's what I mean by snowballing. This is like 2 digits, 2. I mean, I'm sorry, 2 digits. This is 1 digit. This is 2, 2. This is 3. So it could be okay. So what do we do? Quick evaluation using Descartes' rule of signs. This is positive. No change, no change. 1 change, 2 changes. That's not very useful. So there could be two real positive solutions. I never use the negative Descartes rules test, right? So let me run through it real quick in my head. This will be sign change number 1, sign change number 2. 2 sign changes. Oh, that's bad too. So there could be up to 2 real negative solutions. Or there could be zero real positive solutions. I'm not going to explain it. Technically, I never did a stream talking about it using Descartes' rule of sign. So, too bad. maybe we'll revisit it one day. But it's kind of tedious. Alright, so here we go. Let's just use standard 2 or 1. Judging by the numbers, they're kind of... Oh, 2 is going to snowball too much. Let's test 1. Classic 1. 6. This is already looking bad. It's looking bad. It's looking bad. Maybe not. 151. No, it's not good. It's the dream is dead. -4. That's a puny -4 right here, which is insufficient for this one. Okay, but that's pretty good, right? 46 remainder, positive remainder. So that is not a bad first guess. At least it ain't something wacky like 1000, right? Okay. So the fact that this... Okay, so what do we get? We wanted to achieve 0 in the end, which means this needs to be a larger magnitude negative, which means this needs to be smaller, 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 which means this needs to be smaller. Yeah, okay. So therefore, we are going to try either 2/3, 5/6, or 1/2. Let's try 1/2. I have great confidence that 1/2 will work. (6), 53, 82, -55, 50. Oh, let's see. I really hope it works. This is super tedious. 28 summation 110. You know what? Did it actually happen? Half of that is 55. What? Are you kidding me? Second. Okay, well, second try technically. This is the first try. This is the second try. Okay. I'll take it though. So we have a remainder 0, which means we have a positive real solutions, which means because of Descartes' rule of sign, since we found one positive real solution, then there must be another, there must be a second positive real solution. Very good. Very good, very good. But let us clean this up real quick by factoring out the 2 from those ones. Well, technically we could just continue on with synthetic division, right? But let me factor out 2 to put it right here. So again, technically, because this is a 0, then it is x minus 1/2 is our factor. We're going to steal a 2 from those ones to beautify that one. So these ones change to 3, 28, 55, negative 50. To bring the 2 here, which thereby gets us 2x minus 1. Can we use other algorithms at this point? No, this is x power 4. This is still x power 3, so we can't treat it like a quadratic, unfortunately. Okay. That is unfortunate. But don't forget, those are technically coefficients for x cubed plus 28x squared plus 55x minus 50. So this is our next thing to attempt to factor. Again, we know that there's a second positive real solution. And all these candidates are no longer good. You'll have slightly fewer candidates. Alright, so let us begin anew. Let's extract those coefficients. 3, 2, 1, 0. Yes. There they are. Shall we try 1/2 again? No, because we can't take half of 3, unfortunately. What do we have? Do we have 1/3? Maybe 1/3 works. Let's try 1/3. Because, let me think about that. 1/3? Is that going to be good? No, because this is 29, and 29 is not divisible by 3. So 1/3 is a bad guess. Maybe 2/3? Do we have 2/3? There's a 2 in here, and there's a 3. Yeah, we have 2/3. Let's try that out real quick. 3, 2. That looks pretty good, right? 30? 20? Really? We have 75. Oh, I can't believe it. 25 times 2 is 50. What do you know? Second try yet again. Alright, perfect. Okay. That means that since this produces 0, then this is a 0. Transforming it into a factor is x minus 2/3. This is the remainder. It's a quadratic, right? So we should probably beautify this by dividing 3 from those ones, right? So divide by 3 is 1, 10, 25. We'll transfer the 3 over to there to beautify it, thereby getting 3x minus 2. Alright, leftover quadratic, we have x squared plus 10x plus 25. I hope you recognize this. This is a, what's half of 25? I'm sorry, what's the square root of 25? It's 5. What's 5 squared? It's that one. Hey, it's your perfect square. Trinomial. Perfect square trinomial. So let's put this here. And we'll copy paste this junk. Right there. Alright, so this problem wasn't as bad as I had anticipated. Definitely the previous problem was way worse. Alright, so we have this one. Again, it's a perfect square. Half of this is 5. 5 squared is 25. Again, half of this is positive 5. Square. That's the algorithm for factorization of a perfect square trinomial. I think that's what they're called. Final answer. Fully factored form. We're done. Let's take a quick check. Quick and dirty check. This is 25. 25 times 2 times 1. Negatives cancel. So it's going to be 50. Yes. This is going to be 2x times 3x times x squared. So that's going to be 6x power 4. So I'm just checking first term and last term as a quick and dirty check. Yeah, looks legit. Okay, so I have great confidence that this answer is correct. So we'll keep it. Good to go. Cross that out. It does feel good to cross out things that have been finished. Alright, let me do a quick hydration. I feel like I've been talking for like several hours at this point. What is the timer? Let me see. I've been streaming for 3 hours. Wow. Okay, pretty good. Alright, so we'll finish up the last of the problem set for just x. And then we'll move on to x and y situations. Alright, so last problem of this particular set. We have 5x power 4 2x cubed, the negative, minus 135x plus 50. I'm sorry, 54. So 4 terms, maybe this is suspicious. Maybe we can use factor by grouping, right? Check the factors as usual. There should be a 5 and 2 in the inside here and inside there if we can factor by grouping. This is kind of beefy though, so that's going to be a 5 times what? Because we want to match it up with a 5, so that's why I put a 5 here right away. And it ends in 5, so probably correct. So how many 5s in there? 27. Yes. What do you know? So this is a negative 2, so this has to be 27 times 2. Yes. Okay, so this is strictly factor by grouping. That was pretty conclusive early on. Again, biggest clues, you have even amount of terms, and then you check the factors, making sure that there are common factors shared across groups. So this could be one group and this could be another group. You don't have to put them in those groups. You can group those two together and group those two together if you wish. But again, I am not going to do it like that for arbitrary reasons. So grouping those two, factoring from the first group, x cubed, that's it. Because the 5 is prime and the 2. So factoring from here, we're going to factor negative 27 from those two terms. So negative 27 is brought out, and then we have left over 5. Don't forget the old x right there. And then we factor out a negative 27, so the sign flip occurs, so that's negative. And lastly, 2, yes. So you can see this group here perfectly matches the group there. So looking really good. Slap on the old brackets. We have term number 1, term number 2. They both share this 5x minus 2 factor, so we can bring that out of the brackets. 5x minus 2. Always put parentheticals, brackets. Don't stop here though. Take a quick survey. This one is fully factored. This is a difference cube number 1 and cube number 2. So use your favorite factoring algorithm. I'm going to do the shortcut. Cubic root of that is just x. Cubic root of that is negative 3. Square that. Get first term. This one times this one. Flip the sign to get this. Finally, square that to get the third term. Fully factored form. Perfect. Copy paste the first found factor. First found factor. All that alliteration. Alright, so we have factor number 1, number 2, and number 3. This one you cannot factor anymore. Discriminant test if you wish. Yeah, it's already negative. We are good to go for this problem. Perfect. That was better than I thought it would be. Again. Cool. I thought it was going to be order of increasingly more difficult, but I guess I had just forgotten. Okay, we're going to take a short... You know what? Let me think about this. Shall I end it here or should I take a short break? Yeah, I'm going to take a short break, maybe 5 minutes. So I'll be back after eating a cookie. Alright. That was basically the main purpose, was just to get a little bit of sugar. I did not eat a full cookie because it is kind of light. And also to move around. Yep. Yep. Alright. Let us resume the situation. So I guess that was a good intermission. Wait, it wasn't even 5 minutes. That's okay. Alright. So we have finished factorizing a bunch of problems involving just x, a bunch of polynomials, anything ranging from difference of two squares, difference of two cubes, sum of two cubes, grouping situations, generic situations, weird situations. So a lot of work involved, but we are past that, and now let's get to other similar situations, but now we have x and y. So first problem up, we do have this one right here. It's going to be 12x cubed, and then minus 32x squared minus. Now here's where it's different. 3x y power 4. That's kind of funky, right? It's okay. It's pretty much the same strats as before. Are we having an earthquake? There's like a slight shaking. Okay, interesting. Or maybe I'm just jittery. That is the problem. We have 4 terms. This is not a typical factoring situation, but I hope you recognize the similarities. We have group number 1, and then we have group number 2. This is y power 4, y power 4. Very suspicious, right? This is a 3 and 8, so there should be a 3 and an 8 inside there. Is that true? Yes. So factors of a 12, 3 times 4. 4 times 3, I would prefer to say. So that 3 lines up with that 3, and then here we have a 4 times 8. This 8 lines up with that 8. So perfect. The grouping is good. That cookie was a little too starchy. Now we have this one here matching up with that one there, so that's going to be the group. So from the first 2 groups, we're going to factor out 4x squared. Greatest common factor. Generating 3x. 8. Perfect. From here, we're going to factor out a negative y power 4. Thus generating 3x, sign flip, sign flip. There we go. So, are we done? No, we're factoring by grouping, so slap on the old brackets. Term number 1 contains this factor. Term number 2 contains that factor. So, bring it out. Typical situation. Parentheticals. Very nice. Here we go. But we ain't done though. This one is fully factored form, but this is a difference. Perfect square number 1, perfect square number 2. So use your factoring algorithm for a difference of 2 squares. It doesn't matter that we have a y here, it just behaves exactly the same way. So square root of that, square root of that. We're going to take that, copy paste. All you need to do is flip the signs. Plus, minus. And I think that's it. So copy paste this one. Do we have any more to do? Nope. This one is a sum. Is it a cube? It is not a cube. This is a difference. This is a square? Yes. If this is a square? No. So we're pretty much done. We are good to go. However, if you wanted to go farther, could we go farther? Yes. So you can actually factorize this into root 2x. But this is not good because typically most teachers would not want you to have rad x. You need to have x as with a whole number coefficient, and this just doesn't do the job. But technically, can we put this? Because technically it is a difference. This is just not a perfect square, but you could factorize into that one. So this is technically true, but again, I don't think anyone wants this answer, so we're gonna leave it. We're gonna omit it, leave it out, and we will keep this times this times this. So I think that's good to go for that particular problem. Just a straightforward, well, not straightforward, but it's just a classic difference of two squares scenario. We're done with that one. Okay. Brilliant. Oh, this is actually kind of annoying. Hold on, let me move this. Alright, there we go. This drawing program is very old. It is Sketchbook Pro, I forgot what year, maybe 2013, maybe 2011. You know what, let me look it up real quick. Yeah, Sketchbook Pro 2011, where you don't draw with vectors. So if you try to enlarge or shrink something, it gets all screwed up. It gets like information loss, which is very sad. But I've been using it for how long now? 12 years. That's okay. Still better than MS Paint. Alright. Maybe. Next problem. We have x power 12 times y power 6 minus 1. If this feels like a familiar situation, it should. We have a difference of what? This is a perfect square. This is a perfect square. This is also a perfect square. So difference of two squares, right? Or difference of cube, because the cubic root of that is x power 4. Cubic root of that, y power 2. Cubic root of that, negative 1. So, which root shall we take? We already answered this a while back. We're going to do the difference of two squares first. Because if we do a difference of two squares first, we would generate two cubic situations. But if you use the difference of two cubes first root as the root, you're going to end up with a difference of two squares and a funky polynomial. So that will not be the right root to take. So let's treat this as a difference of two squares first. So square root of that chunk is going to be x power 6, y power 3. The 1. We shall copy paste that. Again, difference of two squares. This is going to be minus, this is going to be plus. You can redistribute to do a quick check. These two middle terms will cancel out. This one times this one. Yes. This one times this one. Yes. So, successful first factorization step. This is a difference of cube number 1, cube number 2. And this is a sum of cube number 1, cube number 2. So, just use standard algorithm at this point for sum difference of two cubes. Cubic root of those two. Just divide each exponent by 3. That's easy. Keep the same sign. Now here comes the algorithm. This thing squared gets the first one. This one times this one, flip sign, takes you to this one. I'm going to drop the 1. Lastly, this one squared takes you here. We're finished with the first. Now factorize this junk. Same strat, you know. I'll go through the entire motion. So cubic root of those ones, just divide exponents by 3. I'm going to drop the 1. Cubic root of positive 1 is just positive 1. Here's the algorithm yet again. Square this one for this. first term times second term, flip sign to get this. Lastly, square that one to get this one. Alright, so we should be finished. This one is in a difference of 2 squared. This is a perfect square, but this is not a perfect square. This is a whole number 1, so if we break it up anymore, we're going to get fractional exponents, so leave it alone. This one's not factorizable. Following difference of 2 cubes algorithm, this one, it's a sum. This is not a cube, so we're good to go. This one's not factorizable. So we are good. Finished with this one. Again, if we went the other route by changing this into, if we first had factored it using a difference of 2 cubes, you will get a difference of 2 squares and something that's atrocious. That's very difficult to factorize. I don't have a good factoring algorithm for that one. So we're done with this problem. So again, given a choice between interpreting a situation as a difference of 2 squares or a difference of 2 cubes first, always go with difference of 2 squares first. It makes things much, much easier. So crossing that one out, we have 1, 2, 3, 4, 5, 6, 7 problems. That's pretty good. Some of them are a lot easier than other ones, though, if I remember correctly. Alright, first problem. I mean, not first, the third problem now. We have x cubed y power 1. That one is there, and then we have the xy cubed, and then plus 3y squared. So already, take a quick survey. There aren't a whole lot of factors to break down. This is exponent 3 for x, 2, 1, 0. Exponent 1, 0, 3, 2. That's interesting. There are 4 terms, 1, 2, 3, 4. They seem to have things in common. Right? You see it? I hope you see it. This is coefficient 1 and 3. This is coefficient 1 and 3. So this is probably factored by grouping. So I'm going to group those two, group those two. For the first group, we can factor out x cubed. I mean, x squared. That's it. For the second group, we can factor out only y squared. Thereby yielding xy plus 3, that's it. So take a quick step back. We have term number 1 and term number 2. They both share the same factor. So thus we can factor it out. So slap on the old brackets, factor out the parentheticals. Take a step back. Now we have a sum of 2 squares. There's no algorithm for that one, so no more factorization here. They're all exponents 1, so we're good to go. This is finished. That was easy. Crossing that one out. Alright. Easy. Next problem up. We have 27x to the power of 9. Probably a cube, right? And then we have 64 with y cubed. Only 2 terms, so that's not too bad. There's a sum. This is a cube. That's literally 3 to the power 3. This is a cube. That is x to the power 3 to the power 3. This is a perfect cube. This is a perfect cube. Alright, so this is a sum of 2 cubes. So we're going to use a standard situation. Standard factorization. So cubic root of that is 3. Cubic root of that is x power 3. Cubic root of that is 4. Cubic root of that's easy. It's y. Close parentheticals. Use the algorithm. Square that. This one times this one with a sign flip. So that's 12. That's easy. Just copy paste the letters. Lastly, take this one, square it. get the last term. And that should be it. There's a sum. This is a perfect cube. That's nothing. So good to go. This one is almost never factorizable, so we're good. If this one was factorizable, we'd be able to factor it in the beginning, probably. That's my assumption. But, you know, I don't want to bother. I think of all my experience, I've never been able to factor this leftover part after doing the difference of two cubes, or sum of two cubes, except for really weird problems. Like the ambiguous situation. Do you use difference of two squares first, or do you use the difference of two cubes first? But you saw we can circumvent that by doing difference of two squares first. So this one shouldn't be factorizable to my knowledge. So we're good to go. Cross it out. Alright, that one has 3 stars, so I'll save it for last. And then we have 4 more problems. I guess we have some sort of order. We're going to have, what do we have? 8x squared minus 42x times y plus 45y squared. Okay, take a quick peek. This looks kind of weird, right? Because we haven't really dealt extensively with multiple variables. But I hope you recognize this, right? Well, actually, is this a thing? No, this is not a thing. This is 8. And this is 45, this is x squared, this is y squared, this is x power 1, and this is y power 1. So this is like, similar to foiling methods that we've already learned. And here's what I mean. I mean that this is like, this thing right here is like something x, and then this one is something x. You know, you do the same thing, the same treatment for y squared. This right here is probably a y thing, and that's also a y thing. Because if you multiply this one times this one, you get something x squared, and that something is supposed to be 8. And same thing is true for the y stuff. It's going to be y thing number 1 times y thing number 2 should give you 45 y squared. And then, more importantly, getting this thing in the middle. You see how this here is an xy term? And so is this one times that one. Also gives us something xy. So, treat this exactly like how we treat a typical quadratic situation. So, we're just playing around with the factors. What are the factors of 8? 8 and 1, 4 and 2. What are the factors of 45? 45 and 1. That's a 3 times 3 times 5. Ordering is nice. So 3 times 15. And then we have a 5 times a 9. And I think that's it. So playing around with these factor combos, can we produce a negative 42 if they're the same signs? Probably, right? Let's test this one real quick. 20 and 18. What's that? 20 and 18 is 38. We're fairly close, so not a bad first guess. Let's try this one. 30 and 12. Yes. So this is the correct combo. So these are the coefficients that produce the 8. So therefore it must be a 4x there and then a 2x right there. So again, these two have to multiply to become that one. So these are the y coefficients that produce 45y squared. Same strats as before. The 4 here has to be multiplied to the 3 there. So the 4x here has to be multiplied to the 3y. We're just tacking on an extra y for the ride. Right. So this gives us a 12xy, but we want a negative because both signs are the same and they're both negatives. So this is negative. And then the 2 here gets multiplied to the 15y there. And again, both sides are negative. So should be it, I think. So we have successfully factored this quadratic-like thing into this thing. So good to go. Quick check. 8x squared, yes. Positive 45y squared, yes. This is negative 30xy, negative 12xy, yes. Fully factored form, we're good to go. Not too bad. Alright, what's the next good one? That's a trick problem. I still remember it, writing it up. Okay, this is a weird problem. No, it's pretty standard actually. So we have 2x squared minus 3xy plus y squared. I think this is just similar to the previous problem. So again, the idea is like a quadratic. This is like an x thing and an x thing. This is a y thing and a y thing. We can tell by the exponents that one arises from the product of those two. This arises from the product of those two. And you see how these are x power 1, y power 1? They arise from the summation of those two products. Alright, so that's the idea at least. Let's see if we can make it real. So we have a 2, 1 only. This is only a 1, 1. What do you know? That already makes a 3. This is a 2 and this is a 1. Both signs are the same. Both signs are negative. So, pretty straightforward. Those are the coefficients for the x's. Those are the coefficients for y. They're both 1s. They're both negative. Both signs are the same. They're both negative. There it is. That was easier than the previous problem. We didn't even need to do very much. Finished. Okay, spot check just for good form. These ones give us positive y squared. Check, check. This is negative xy. This is negative 2xy. So together, negative 3xy. Yes. Check, check. Check off everything. It's fairly satisfying. Alright. Cool. What problem was that? Oh, I already crossed it out. Silly me. Silly, silly me. Alright, next problem up. We have this okay looking problem. It's going to be x power 4 minus 16y 4 plus 4x squared plus 4. Alright. So 4 terms right off the bat. So this is not a quadratic-ish looking situation, probably. What do we have? Is this factored by grouping? We have 1, 2, 3, 4 terms, but the coefficients don't look nice. This is a 1, this is a 16, this is a 4, and this is a 4. That's not looking good. Right? Well, you know what? Maybe we could do that. Let's try that. Okay, so basically what I'm thinking about is this is a factor of 1, right? And this is a factor of 4 and 4. So this group together doesn't share very much in common with that group. But what if we grouped this one with this and this one with that, right? That's an idea. So I'm finally moving things around just to test the group. Factoring grouping. So this one gets lumped with that one. I'm just experimenting, and this one gets lumped with that one. But since this is a minus, as long as you keep the minus next to it, we can move it to way to the back. So we'll have plus 4 minus 16 y power 4. Again, I'm forcing this because this is a 1 to 4. This is technically a 1 to 4, but the signage sucks. So this is probably not factoring by grouping. I don't think so, but I'm just curious. So factor out x squared from those two. That's already not looking the greatest. Factoring, again, it doesn't look good because of this different signage. But might as well go all the way through. Factor positive 4. Yeah, that's not a group. This is not a group. Okay, this is bad. Alright, so that's the end of that nonsense. So what do we do with this situation? If we cannot factor by grouping, what can we do? Let me think about this. I think there's a trick to doing. Oh, okay, I see the trick. Yeah, it's just one of those trick problems. Well, you either recognize it or you don't, or you've done enough problems, or someone revealed this problem to you beforehand, but this doesn't have any x's, right? So we could just move it to the back yet again. Let me do that yet again. Thereby, these ones will be moved forward. This one gets moved to the back. And I hope you recognize this. Half of this is 2. 2 squared is 4. Which means this is a perfect square trinomial. It follows the quadratic looking thing, right? So this one you can factorize it into, what's the square root of that? X squared. What's the square root of that? 2. Both signs are positive. Do a quick check. This one times this one gets you this one? Yes. This is 2x squared. This is 2x squared. If you summate, that's 4x squared. Yes. 2 times 2 is 4. So this is correct. So let us condense those two into x squared plus 2. Close. And lastly, minus that junk. But wait, there's more. This is a difference of square number 1 as a whole and square number 2. So, difference of 2 squares, yet again, factor it as such. So what's the square root of this one? You're just literally treating this as one whole thing to exponent 2. So to find a square root, you divide the exponent by 2. So technically it becomes this, but when you have a 1 exponent, just drop it. I'll put the parentheticals actually. And then this is a difference of, so make sure you take the square root of that one as well. Square root of that is 4. Square root of that is y squared. I'm leaving the parentheticals on to make it clear. Alright, copy paste. Typical strat for difference of 2 squares. There you go. Since this is a minus, then one of them has to be a minus, and the other one is a plus. And we have successfully factored this goofy scenario. Final answer, you should probably drop the parentheticals, but I'm going to leave it on again just for sake of where things have come from. Yes. So what I mean is like this. This one is essentially something like a squared minus 16y4. So this is like the a here, and this is like another a, because a times a gives us back to a squared. Alright. Not a bad problem, but it's one of those like goofy problems where you gotta recognize the difference of, you gotta recognize the perfect square scenario. Alright, next problem looks like a real doozy. I put 3 stars by it. Why did I do that? Hopefully I still know how to do this problem. So we have 27x cubed minus 18x squared y2 and 15x squared minus 10x y squared and then plus 6xy. Lastly, minus 4y cubed. So this is a real monster looking of a problem, right? Take a quick evaluation. Well, we have a bunch of terms with a bunch of letters. This is exponent. This is a base x to the power of 3, power 2 again, and then power 1, and then power 0. But this is exponent 2, but this one has a y squared, this one does not have a y squared. So this is very, very messy. Alright, so we can't factor something from all terms, right? Double check. Factors of 27. 3 times 3 times 3. Factors of 18. 2 times 3 times 3. Factors of 15. So we have a bunch of 3s so far. Factors of 15. 3 times 5. Factors of 10. No more 3s. That's saddening. Factors of 6, 2 times 3. Factors of 4, only 2 times 2. Alright. So take a quick survey. We can't factor something from all 6 coefficients. That's okay. And not all terms have x's nor y's, so we can't factor x, y's from all 6 terms either. But the most striking thing is we probably can't use typical factoring problems, right? Because we have the variable x and the variable y. So we can't do standard algorithm. So this is probably a gimmick to the situation. So probably what? We have 6 terms. So probably factoring by grouping. So maybe we can group these, those 3 and then those 3, right? Do they have enough in common? So if you factor a 3 from those 3, then we're going to get 9, 6, and 5. Do we get the same thing here? No, we don't. Right? If we factor 2 from all those, we're going to get 5, 3, and 2. So this group is definitely mismatched with that group. So we can't group it as is. That's very unfortunate, which makes things a little more difficult. But there's a 5 here and a 5 there. So these ones are definitely different groups. Is there another grouping scheme that we can do? Let me think about this real quick. Let's see if we can form groups of 3, but making sure there's similarities. So these 2 for sure need to be split apart, because we can get a 5 here that can match this 5 as long as we factor out a 2 and factor out a 3. So for whatever group contains this one, you have to be able to factor out a 3 from whatever group that contains this one. So this contains a 3. This contains a 3, so maybe pair up those. But these 2 also contain 3s. So we're going to group this one with either that or that. And I don't know which is the better of the 2 just yet. But we'll figure it out. So again, the idea is to group this because the idea is they both have a 5, so they should be in separate groups. And then this one means that we have to factor out a 3, which we will pair up with maybe this one and that one, or maybe this one. But we're forming a trio. Alright. So this one has to be grouped with something factorizable by 2. This is factorizable by 2. So, and then this one has a 2. Okay, I think that's clear. So let's do this one with that one. So we will group those 3 together. This one with this one and this one. So let me colorize it just to make things clear. Let's group those, that term with that term with that term. So let's see what happens if we factor out a 2 from those 3 terms. So we're going to get a 9 times, plus or minus. I'm not going to put plus or minus. So we're going to get, if you factor out 2, you get 9. Factor out 2, you get 3. You factor out 2, you get 2. Will we get that with the other group? Let me see. If we factor a 3 out of those 3, we are going to be left with a 9. That looks good. We're left with a... Wait a minute. This is supposed to be a 5. What am I saying? Okay. Oh, let me continue factoring the red. Okay, so if we factor out a 3 from here, that gets us a 9 first. Factor out 3 from there, we get a 5. Factor out 3 from there, we get a 2, right? That looks mismatched, but I think I screwed up the blue one. Okay, go back to the blue. If I factor a 2 from here, we get a 9. If we factor a 2, we get a... I don't know why I put a 3. That's supposed to be a 5. If we factor out 2, we get left with a 5. We factor out 2, we're left with a... Okay, you know what? That's a perfect match. So we can probably go forward with the grouping, and hopefully the signs will correct themselves, and then the x, y's will also factor correctly. So let us put those groups together. So again, we're putting this one with that one with that one. For group red, and with the 15, and then with this one right here. If the letters don't work out, then it's probably not the way to go. That's red group. And with blue group, we have whatever's left over. So negative 18x squared y squared, negative 10 xy squared, and then negative 4y cubed. The signs are looking really good. See, these are all positive signs. These ones are all negative signs, so we factor out the negative. Wait, why did I put it in blue? Whoops. That looks... it's a little jarring. It's too saturated. Oh. Not what I wanted to do. We're going to take that and put it right here. And remember, you're always entitled to put parentheses around it as long as you put positive around terms. You're always correct. Okay, so let's carry out the actual plan. Again, red group, we know we could factor a 3 from all members of the red group, because that's the way we set it up. But what else can we factor? This is a x cubed, this is x squared, this is x1, so we can also factor out x1 from all 3 terms. This is the only one that has a y. So let's clean it up. So 9x squared, and then 5x, and then 2y. Alright, so that's the first red group. Factoring the second blue group, what are we doing? We're factoring out just a 2, but we're factoring out a negative 2 instead, because they all have negative signs. So we could perfectly match this one. What else can we factor out? This one has a x squared, this is x, no x's, so we cannot factor out an x. This is y squared, this is a y squared, this one has a y squared, so we can factor out y squared. I think that's correct. So that means the groups will probably match. So this one divided by negative 2 is 9. Divide by negative 2, 5, keep the x, y squared is factored out, divide by negative 2, factor out the y squared, so down take the exponent, standard division rule, subtract the exponents because it's matching bases. So let's take a step back. What do you know? Okay, so perfect. We have perfect matching groups. So factoring by grouping is the way to go. So slap on the old brackets. We have term number 1, and then we have term number 2. From those 2 terms, we could factor out this entire chunk factor right here, because it's the same as this one right there. So bring out the parentheticals. Close. And then we have the leftover stuff in the brackets. So 3x minus 2y squared, close bracket. Are we done? This is x squared, exponent 1, exponent 0. So you might be tempted to do quadratic, but this is just a y. Not a y squared, and this one doesn't have a y. So let's leave this alone. There's a difference of what? This is a square. That's irrational. That might be okay, but this one has a whole number, so we don't want fractional exponents. So we're going to leave this one alone. So we're done. This should be fully factored form. Triple F. And that's it for that problem. So quick recap. We start off with 6 terms. This is not a standard polynomial because even though it has x cubed, x squared, we do have the presence of the y factor. So not a typical situation. We have an even amount of terms, so the immediate jump is to factor by grouping. The grouping, if you just do it the way it's written, it's not a good group. So we have to break down the factors just to try to figure out the best groups to form. We have formed the best groups into red and blue. Once we achieve that, you factor out common factors from the two groups. We see that this group factor matches that group factor. So, final step is here, and we're good to go. And I think that's it. Yeah. Okay, no more, I've exhausted all the problems I've written. That's it for factoring. I don't think I'm going to do very much factoring anymore after this one. But when we get to graphing polynomial functions, which is probably what I'll cover next, then we will revisit these skills. So yeah, I guess I will do it again. But, maybe, yeah. I don't know. I haven't made up my mind just quite yet, but I anticipate we're just going to be talking about graphing a bunch of polynomial functions. That one's not too bad, honestly. It just requires some... what does it require? Factoring polynomials and graphing them? Well, first of all, you need the factoring skills, but most of them are pretty nice, in all honesty. And then you need to know end behaviors. We need to talk about that. You need to talk about zeros and x-intercepts. We've technically talked about that a while back. And then we need to talk about what else? No, I think that's it. Okay, so that is the plan for next time. That's it for today. How long did I stream? I feel like it's been quite a while. Let me see real quick. According to 4 hours. Oh, I have to stream for 4 hours. Okay, well, that means I am done. That's it for today. I hope you have a good one, and I'll see you next time.